Hey, hi there. So welcome to the SystemVerilog constraint session. So SystemVerilog constraint construct is one of the core constructs that helps us build coverage-driven constraint random verification, which is what we have been looking at. So we have had a chance to look at a few of the constraints as a part of the FIFO test bench. So in this session, we will go deeper and understand the different facets of this particular construct. Okay, this is the agenda for the session. So we have two parts. So in the first part, we will look at the different features of the constraint construct itself. And then in the second part, we'll look at the methods. So methods helps us activate the constraint. So we will look at that as the second part. So in the constraints, we'll look at how do we use the random variables, and then while forming the constraints, how can we use expressions, and then like a non-random state or config variables. I'm sorry, if you remember, we had used the FIFO config to constraint, right? So there will be few variables which will not be randomized, and they will be just used in the other constraints, and then various operators can be used. So we'll look at those, and then there are some set of special operators that have been defined for building the constraints itself. So we will look at them, and then constraints can be turned on or off. Okay, so constraints are defined statically, but during the runtime they can be turned on or off. So we'll look at how to do that. And then constraints are as a part of the class construct. So and the class constructs, as we have seen, allows us inheritance. So we will look at the effect of inheritance on constraints, and then there is this new concept. I think it has come into the 2012 LRM. There's a concept called soft constraints. So we look at the difference between hard and the soft constraints, and what are some of the use cases. And as a part of methods, we will look at primarily, so if you remember, we have already looked at randomize method in the FIFO test bench, and then we have also looked at inline constraints. If you remember, we had put the constraint for the type as a part of inline constraint. Then there are other two methods called pre-randomize, post-randomize. We'll look at those. And we have other procedural methods that can help you randomize non-class based variables. Okay, so this need not be like, if you want to do something quick, you don't really have to build the entire class based constraint and then call the randomize. You could use these quick system functions that are available. So we look at the urandom range, and then there exists a package called standard which provides you a function called randomize, how to do that. And then there are a bunch of like the different ways of generating scenarios, right? Random scenarios, which you can do it using the rand case and rand sequence. So rand case is a useful construct. It's a weighted case statement. So we have seen a general case statement. So we'll see a weighted case statement. Rand sequence, it is a very powerful construct, but typically in the overall test benches that we build, we tend to use UVM sequence concept rather than the rand sequence construct. But we will just have a look at it and understand what capabilities it provides. Okay, so before we jump into the details of the constraint construct, let's ask ourselves the basic question that why do we need a constraint random? I know to an extent we have addressed this when we looked at like, for example, the counter problem when we went from 4-bit to 256-bit. Why did we need it, right? And then we have looked at how we did the constraint random even in the case of FIFO test bench and how it helped. So we have looked at some of the examples. So we will refresh some of those concepts once again and reconvince ourselves that we need it, and then we'll go ahead with the details of construct. The first question that we need to ask ourselves is, why not just rely on a directed test cases, right? So what does a directed test case mean? Okay, so why do we need to understand this a little bit detail is so that we have to flip the script. That is the idea. Okay, so in a directed test case, what happens is there are two things that remain fixed. So one is the sequence of operations that you create, plus in each of those operations you use certain variables. right? So it could be a series of transactions that you are generating, and in the transaction you have the variable, right? Like for example, in the FIFO, we generated series of push and pops, and the data that we are randomizing is a variable. The delay between operations is a variable. So those are the two things that we were randomizing. So in a directed test case, what happens is the order in which we do the operations plus the values that we use both can remain fixed. In a strict directed, both can remain fixed. Now the question that we need to ask ourselves is, what is the problem if both of them remain fixed? What is the problem? So let's take a simple example that I could have an USB port and I want to test a scenario that the port enters into low power state. I'm not using, let's say I've connected a mouse or something or a USB drive, flash drive, and I'm not using it, and I want it to enter a low power state, and then I want to see how that behaves. Okay, so I can write a simple directed test case. I'll do some traffic, I'll make the port enter the low power state, and then wait for some time, cause some event to come out of the low power state, and then do some more traffic, right? So there's something that I can do. Now, in a complex system, what happens is there is not one variable, there are multiple variables, okay, and there are multiple parallel variables that are in play. For example, when the USB port has gone into low power state, what could happen is somebody could press a reset button, right? And now how does the port behave when it is reset in a low power state? That is again another case. Or somebody could just pull it out, right? Pull out the port. Now that's another case, that while it was in the low power state, what happens if I pull it out? How does it behave, right? And then there are cases wherein a particular faulty device may USB device is a port powered, so it might be faulty, right? Like you connect your phone to charge via USB port, and that particular device might be faulty and it might be drawing too much of a current, and then in its low power, let's say because of some faultiness, it draws a lot of current, and then there's a overcurrent event that gets triggered. So this way there are so many scenarios that can take place, and now we cannot keep on enumerating all these scenarios. That is the problem. So if we could enumerate all the scenarios, maybe we could do even the directed testing, but as a human mind, we have the capacity limitation that we cannot enumerate all possible test cases. And if we were capable of enumerating all possible scenarios, then we wouldn't probably need to even actually write a test case and check it. Maybe we open the RTL and look through and figure out whether it is going to work or not. But that is not possible. So we need the machine to do some level of the random exploration of the design space, so that it can come up with the scenarios that we are not able to imagine. That is the value that randomization brings. So that is the first question. So why not directed? That is the first question that we want. We cannot think of all the scenarios. If we could think, probably we could write all directed test cases and still be done with it, but we cannot think. That is the main problem. Now the second question that comes is, why can't I just do pure random? Why do I have to do constraint, right? Like why do I have to study a constraint construct? Why can't I just let it go, right? Let it just generate whatever it wants. Why is that not useful? That is the second question. So the answer to this question is that there are two things. One is verification is a never-ending is a never-ending work. It never really completes, right? So you define a criteria and then you say it is a complete, but it never really completes. You can keep on verifying a particular device as much as you want. That is because they are so complex. So however much you verify, there is some state space that you can still go through and explore it. So ultimately what we want to do is we want to do the risk reduction, right? So for any type of an application, certain level of risk is acceptable. So we are only trying to do that risk reduction, and hence what we want is, we don't want pure random to just traverse all around, but we want it to focus in the state space that really matters to us. Okay, so that is why we need the constraint. And another quality we need is, like if I just generated a pure random and let's say a particular test case failed, now if I rerun it, let's say it generates another random scenario, that is no use for me. How will I debug it, right? So I also need the ability that it should be able to create a reproducible type of a sequence. So these are the two characteristics that I need because of which just if I do it in a pure random way, it won't be useful for me. Okay, so that is where we have to use the constraint random stimulus as a solution. And through constraints you can limit the state space to the area that matters to that particular application. And second is that there is a concept of seed, which we will talk about it in a little bit more detail as we go through this session. So what the seed allows is, seed is a number that you pass along with your test command line, and that helps test create a random behavior that is reproducible. Okay, so we will look at it a little bit more detail. So with these two things is only when random type of a stimulus starts to make sense in the context of verification. So with this background, now let's look at a little bit more. Now let's look into the details of the constraint construct. Okay, so SystemVerilog, the way a constraint construct has been defined is it works in a declarative way, and because of its declarative nature, it becomes a very compact way to express our logic, and we don't have to worry about the control flow that's required to implement the logic. We just say what we want. We want these like we want random values in this range, and we forget about it, right? So every time we randomize, the simulator will take care of it, right? So that's a declarative, that's what we call by term declarative, wherein we just tell the logic, and we don't tell the control flow to implement that particular logic, right? So that is the declarative programming. We have seen it already in the SystemVerilog assertion. Even the constraints follows the same thing. So whenever you have a declarative programming in play, you always have in the background somebody has to do that work, that control flow, somebody has to figure it out. So that in case of the constraint is something called constraint solver that's built into the simulator. So the simulator has a constraint solver. What it does is it solves the constraints. So it solves the constraints by generating different values and choosing the random values that satisfy the constraint. So that is how the basic operation of constraint solver works. And these values that it generates comes from something called SystemVerilog PRNG, and that stands for your pseudo-random number generators. And as we talked about in the previous slide, this PRNG, which is your pseudo-random, because you're not doing, there's no real pure random number generation. So you can explore a few of the, like how the random number generation algorithms work. So you will understand that much better if you are keen. But this pseudo-random number generator is started with the initial seed value, and that seed value enables it to generate a consistent reproducible random numbers. Okay, so that is the main idea of the pseudo-random number generator. So with the same seed value and the same test bench, this is also important, because if you change the number of calls to the random number generator, then the values generated could be different. Okay, so that is why with the same seed value and with the same test bench, SystemVerilog simulator produces the same random values, right? That is where the behavior becomes reproducible. But if at all the test bench changes, that you change the order, okay, instead of doing low power later, you do the low power first, and then you do some traffic, and then you change the number of traffic that gets generated. So the total number of randomized calls changes, and then you recompile it, and then you rerun the simulation. Then the stimulus generated is not guaranteed to be exactly same. Okay, you could have changed it somewhere else, but as the order changes, then it is not guaranteed. Okay, so there are ways to minimize this disturbance, that you change something and everything falls apart. There are ways to prevent it. We will discuss about it to some extent, but if you change it, then the guarantee is void. Okay, and then there are different versions and the different vendors, right? Like within the simulators, vendors do keep releasing different versions, and there are different vendors, right? So like we have the Synopsys VCS, we have Cadence that is providing the NC Verilog, and then we have the Siemens who is providing us the QuestaSim. So different vendors might produce different results while satisfying the constraints. Okay, so across vendors that's not guaranteed. What is guaranteed is if you take a same constraint random test case and run it across 3 vendors, then it's not guaranteed to produce exact same numbers, but it will satisfy the constraints that you have specified. Okay, and then constraint solver can fail due to inconsistent constraints or invalid inputs, because you rely on certain configuration, or and then you define, like let's say you define a random variable, and one constraint you say a should be greater than 10, and in another constraint you say a less than 10. That cannot be satisfied. So when that happens, the constraint will fail. That is why you should always check whenever you do the randomize. If you remember in the FIFO test bench, we either did if the transaction object dot randomize, or we said at least assert transaction object dot randomize. So we need to always check, because randomization can fail due to inconsistent constraints or invalid inputs. It might be relying on another object, and that object might not be initialized, and it could be a null value, and it tries to access the null object with some variable. It could fail, right? So constraints can fail, so you have to always check after the randomization. Okay, so the overall complete constraint random stimulus generation works in 3 parts. So the first part is we need to declare the properties that needs to participate in the constraint random stimulus generation with either the rand or the Randc keyword. If you don't do that, like for example, this on the line number 10-bit error, this particular property or variable is not going to participate in the randomization. So first step is you declare the variables with the rand or Randc keyword, and the second part is you add the constraints. Okay, so here for example I am adding a constraint on this address field, saying that the lower 2 bits of this particular address field should be always 0. So that makes sure that the address that I am generating are word aligned. So word meaning 4 bytes, right? So if my address, when I have a 4 byte, so it will be the first address will be 0, and the next address will be 4, right, and the next address will be 8, so on and so forth. So the lower 2 values will always be 0. So that is what I want. So I am saying address of 1:0 equal to 0. So this is the constraint I am applying, and I am using the logical equality operator. So all the operators, as we talked about in the beginning, can be used in the constraints. And then I am randomizing this delay bound. So I'm saying delay inside, and I'm giving a range over here in the square brackets 1:20. So now with this, the delay can take any value between 1 to 20. So if I had not added these constraints, if I had left them unconstrained, that is I declared rand address and then I declared rand delay, and if I didn't add any constraint, then what would have happened is an unconstrained rand variable can take any value. Okay, that particular data type, whatever it allows, it will take any value. So in which case my address could have taken the lower 2 bits values which were non-zero. And also note that although I have declared the variables of the type logic, it will still take only 2 state values, because the constraint solver only supports 0 and 1. It doesn't support x and z. Okay, so it won't support it. The third step is the step called randomize. So what you do, so I have declared a class. In the class, the first thing I have done, whichever the variables that needs to participate in the randomization, I have declared it with either rand or Randc keyword. Second, I have added the constraints to make sure that they target the right state space. The third step is I create a transaction and call transaction.randomize. That is the third step. So whenever I call this .randomize, which is a built-in function for every class, it causes the new values to be selected for the random variables. Whatever the properties that I have declared it as rand, they will get a new variable. Every time you call randomize, they will get a new random values. Okay, and the constraint solver, what it will do is it will select among those random values such that they satisfy the constraints that you have specified. Okay, that is what the constraint solver will do. And then, as we have seen in the previous slide, anytime we randomize, there could be failures. The constraint solver can fail, so we must check the results before using it. Okay, so that is a thing that we need to take care. And this part we have already talked about it, that if you don't use constraints, then it can take any value that particular data type supports. And if you have not declared any variable without if you have declared a variable without a rand or a randc keyword, then that value of that particular variable remains unaffected by the randomize call. Okay, only the variables that have rand or a randc keywords are affected by randomize call. The rest of the properties, they do not get affected by the randomize call. They retain, they are called as state variables, so they retain whatever the value that they were holding prior to the randomization. So this is the basic idea that how you do the constraint random stimulus generation. It's a three-step process. You declare rand or randc properties, and second, you add constraints so that overall values that particular data type can take is trimmed to target the area that you care for. And third step, you create an object of the type whatever the class that you have defined, and then call the dot randomize function. And when you call the dot randomize, the rand variables that you have declared within the class will take the random values which will be as per satisfying your constraints that you have defined. So that is how the overall constraint random stimulus generation works. Okay, so we have been looking at how to build a complete solution for the constraints, and in the previous slide we have already taken a look at it. It's a three-step process. The first step, defining a rand or randc variable, second adding the constraints, and third calling the randomize. Now we will add one more dimension to it from the overall how do we build the overall solution point of view, and then we'll go into the details of each of these aspects, like how does the randc behave, how does the various operators that we can use within the constraints, and so on and so forth. But coming back to this overall solution point of view, let's add the inheritance angle from the class point of view. When we did the inheritance, we know that when a particular class extends a base class, all the functionality that is present within the base class becomes a part of your extended class that we have already seen. And then you can extend functionalities in two ways. Now you can add more new methods to the derived class, or you can override an method in the base class, either add new functionality to it or replace it with a newer functionality, right? So if you wanted to add the new functionality to it, you call the base class function as well, super dot whatever the corresponding function. So now you have the base class functionality, plus thereon you can add the newer functionality, right? So that is how it worked in the case of inheritance. Now we want to understand how does it behave in the context of the constraints. First of all, naturally, all the properties that we have declared, although we might have added the qualifier rand or randc, they become part of your the subclass or the derived class. They already become a part of it. And not only they become part of it, even the constraints that we have added in the base class become a part of your subclass or the derived class. Now, as per the inheritance rule, now we can do two things. One is we can add new constraints. Okay, so we can add new constraints to the same variables that we had declared it in the base class. Okay, so if we add new constraints, then the constraint solver has to satisfy the constraints that are present in the base class as well as the constraints that are present in the derived class. It has to satisfy both of them. That is one thing. Second thing is I can take an existing constraints which was defined in the base class, and I can override it with a different type of a constraints. That is possible. So note here that I am not adding, I am replacing. So how do I do those two things, right? So that is what we will look at in the context of constraints. So let's understand that with the help of an example. So we had looked at an APB transaction in the previous slide. So now what we will do is we'll extend that particular APB transaction. So we are creating a new class APB transaction underscore ext that extends the APB transaction, or the APB transaction becomes the base class or a parent class. And then what we are doing is we are adding one new property which is of the type rand called address type, and we have declared this address type to be of this user defined enumeration data type which contains these three named constants low, mid and high. So I have declared this new property called a type, which is of the type address type. Okay, then I'm adding a new constraints. Okay, I'm adding address range constraint. So in the previous example, if you remember, we had only the constraints for the alignment, right, wherein we had made the last two bits of this 32-bit address as a 0. So that's the only constraint we had in the base class. Now what we are going to do is we are going to add some range constraints over here. So I have added this new property which is of the rand type. Now whenever I randomize it, since I do not have any constraints on the A type variable itself, it can take any of the three values that I have defined. Now whenever it picks any of these three values, for each of the value I am defining additional constraints on address. So if the A type takes a value low, and then what I want is my address to be in the range of 0 to 15. So I'm using an implication operator over here. Just hold your thoughts, just understand that it behaves like an if condition for now. We'll look into more details. There's nothing more than if condition, but we'll look into it specifically more in the subsequent slides. So then if the A type takes a value mid, then we say address has to take this middle range from 16 to 127, and then if A type is high, then I add 128 to 255. So this way of doing constraints, what it does is it provides you a better control, right? Because now A type can take any of these three values, and based on these three values you have much better control of spreading the stimulus across these ranges, rather than like the entire 32-bit with excluding lower 2 bits getting randomized. Almost all the 30 bits were participating in the randomization in previous case. So now we are able to control it with the help of A type. So now notice that what happens is now address rand variable now has two constraints, right? One in the base class, for which we did it for address word alignment, and this new one for this address range C that we have added. Now the solver has to satisfy both of them. That is the first thing. Second thing is we have now added another constraints on the delay bounds, right? So the delay bound was the name of the constraint that was already available in the base class. Now I have overridden with a different value, right? So I'm saying delay should be inside 20 to 30. Now what happens is this one, because the name of the constraint in the base class and derived class is same, the derived class constraint overrides the base class constraint, right? So now only the derived class constraint will take effect. Okay, so there's no way you can say base class constraint plus this one. If you want to do that, then you have to give a different name, right? If you use the same name, then you have no way to extend that. You tend to completely override it. Okay, that's what happens in the case of constraints. Apart from this, there is another way to add new constraints to the existing constraints. That's called as inline constraints. So we have seen this to an extent in our FIFO test bench as well. So this one is something you add when you are actually calling the randomize. Okay, that is something like very specific behavior that is applicable to a specific test scenario. You don't want to add that as a part of your generic transaction or a generic sequence, and those additional constraints you can directly add it in the test using the inline constraints. An inline constraint is similar to adding this another constraint on the variable. It's additive, right? So that's why I'm showing this arrow over here. So now when I add an inline constraint, it has to satisfy the existing constraints in the base class, derived class, if there are any. Along with that, it has to also satisfy the inline constraint that I've added. It's not overriding, it's additive, right? So here when I say I randomize with A type equal to low, if I had any other constraints over here, it had to satisfy that plus this. Like here, for example, if I say address greater than 10 and address less than or equal to 20, then still here I am able to I can satisfy this particular constraint still, right? So I can satisfy this. It should be now what will happen is the address type can never take a value of high because of this inline constraint. Now address type cannot take a value of high. It will be forced to take either a value of low or mid, and it will be in this particular in either of these two ranges because of this additional constraint. Okay, and here one more thing I am just showing, like if I want to generate data which is always a power of 2, then I can do this particular expression that I can say data and with the data of -1 should be equal to 0. So when you do this, you can put in some numbers and work it out. It will always lead to a power of 2 numbers. Okay, so I can add this also as an additional inline constraint. So this is how in the scope of overall solution, along with the 3 steps process, the inheritance plays the role wherein you can either add new constraints in the extended class, or you can override an existing constraint and replace it with a new constraint by using the same name. And also you can add additional constraints by using inline constraints, and those are helpful for the test scenario because that's only scenario specific. Then you call it with the inline constraints. Okay, let's just once quickly summarize the inheritance part because that was a long description. The derived class actually inherits all the constraints from its superclass or the base class, and then constraints with the same name in the derived class replace the same constraint from the superclass. So this is something we saw. And constraints with a different name on the same variable will add the additional constraints, or for the different variable also. So they add to the additional constraints that the constraint solver needs to satisfy. The name is same, it's a replace. If it is a different name, they add to the constraints that are already defined in the superclass, and the constraint solver will have to satisfy both. And then actually this is one more thing, like a virtual or abstract class. We had not discussed that in the previous context. If you have a virtual or abstract class, if you remember, we used to add like a pure virtual methods in it, which then there was an obligation for the derived class to implement those methods, derived class which is of non-virtual type, to implement those particular pure virtual methods. The same concept can be applied to constraints as well, that you can just declare pure constraint and just give the name of the constraint. You don't even have to tell which variables and any other details. So you just say pure constraint and name of the constraint, then it provides an obligation for the non-virtual derived class or a non-abstract derived class to implement that particular constraint. Okay, so from here onwards, we will look into the details of each of the three steps that we have talked about. The first step we had talked about was declaring the random variable. So we will now look into a little bit more detail of what do those mean. So let's compare rand versus randc. We have not talked about randc or a rand in detail, so let's understand them further. So a variable declared with the rand keyword are standard random variables, okay, and their values are uniformly distributed over the range. So whatever the range that you constrain, or if you don't constrain, then all the possible values that a particular data type can take, they will be uniformly distributed. Okay, uniformly means every value will have an equal chance to occur. That is what it means when we say it is uniform. So if I had a random variable, random bit 7:0 of a, it's a 8-bit unsigned int, which means that the probability of the same value repeating on a successive calls to randomize is 1 divided by 256. So everyone is getting an equal probability. Whereas when you go to randc means rand cyclic. Okay, so cyclic variable that cycle through all the values in random permutation of their declared range. Okay, so for example, if I declared a randc bit 1:0 of y, then it has to what it does is, as a first step, it computes the range of values. In this case, the range of values is 0 to 3. Now on successive calls, right, so it returns the values in particular order. Okay, so and then what happens is that after the last element of that particular permutation, it repeats the process of computing new random permutation, so that these values will be created, the range will be created, and it will be sort of arranged in some random order, and then one after another they would be returned on its successive calls, right? It's more like if you remember, we had this shuffle function on the it's an array method, right, which randomly ordered the array. So every time you figure out what are the range of values that it can take, shuffle them, give them one after another. After the last value has been given, you again take the whole range and shuffle it again. That is what the Randc will do. It will ensure that all the values occur before any repetition takes place. So that goes through cyclically. Whereas when you have the rand, that is not what happens. So a particular value could appear multiple times before it could happen. Okay, although the probability is uniform, that doesn't mean that it would never repeat before the other value. Statistically, it is uniform, right? But whereas in case of the Randc, what will happen is every value will get chance to occur in some order, and then only when all the unique values are exhausted is when you go back and repeat it again. So that's what the Randc does. And then what happens is, in the Randc is a more stricter constraint. So in the constraints we will see this eventually. The stricter, whoever has a stricter requirement is solved before. So Randc is more strict, that the unique values have to first complete before they repeat. So they are always, the Randc variables are always solved before, and then even so, one more interesting aspect with respect to Randc is that if the Randc variable is declared as a static, then the Randc state variable, right? So it is the nature of its staticness is across all instances, right? So now how do I say this is, like, for example, if I have a static variable, if I have multiple class instances, then its cyclic nature is across all the classes, right? So I randomize this object 1, I get a particular value, a randomized object 2, the next cyclic value will show up in the object 2. So that is what it meant by the Randc state is cyclic. So if I randomize, let's say, 4 objects which contain this type of an variable which can take 4 values, then all the 4 values could be across different objects. It need not be within an object if you are declaring the Randc variable to be of the type static. Oh, let's look at some important rules with respect to constraint block. Okay, so we have now started looking into more details of each of these aspects. So we looked at the first part, that's the Rand versus the Randc. We understood. Now we are moving to the second part, wherein after declaring the random variables, we need to create the constraints on them, right? So now we look at the constraint, and then we'll go deeper into the constraint. Okay, so constraint block, what the constraint block means is constraint keyword, name of the constraint, and then you have the curly braces, then you provide some expressions, and then you end the curly braces, right? So this constraint keyword, name of the constraint, and this 2 curly braces, the opening and the ending one, right, they together is called a constraint block. Okay, so now what are some of the rules associated with the constraint block, the important rules? There are many. I am summarizing or looking at the important ones. So the values of the random variables are determined by the constraint expressions that are provided in the constraint block, right? That we saw, like if I said delay should be inside 1 to 20, then it is it is that expression will guide how the random value should be chosen for the random variable delay. That's what it means. That's the job of this particular constraint block anyway. That's a primary responsibility. Now the second thing is constraint blocks are class members. What does that mean? Very similar to the way we were saying the properties and methods of the class. Even if you remember, when we had discussed about the class properties and methods, or like what can be contained in the class, we had mentioned that the constraints and functional coverage also can be a member of a particular class. So here we are saying that the constraint block are also class members. What that means is they can be accessed using the dot notation. Any class member can be accessed using the dot notation on the object of that type of class. So I can take an object of class and say the object name dot the name of constraint block, I can say that. And you may ask, what is the use of doing that? The use, we will come to it. So actually we can turn on or off a constraint using a constraint mode construct associated with the constraint block. So we look at that, but they are the members of the class. Okay, and constraint block names have to be unique within the class. So you can actually use the same name when you extend a particular class, but within a class all your constraint block names have to be unique. And there can be multiple constraint blocks declared within the class. You can have multiple, if you see, remember we had address alignment and the delay constraint when we were looking at the APB transaction. So we can have multiple constraint blocks within a class, and then of course they have to have unique name. And you can actually have multiple constraints blocks on the same variable as well. There's nothing prevents you from doing it. You can do that. Okay, and it's generally a good practice to use at least one constraint, not at least, you should use one constraint block per random variable. What that means is try to avoid putting multiple logical constraints or like multiple constraints on multiple rand variables within the same constraint block. Okay, that's what it means. And you may ask, why do I need to do that? Then, as we talked about, if I want to use a constraint mode on the particular constraint, then if you have multiple variables, generally you want to control one particular variable, right? So let's say I don't want randomization on address, or I don't want randomization on delay. Then if we have constraints per I should not say randomization, I should say I want to control the randomization on that particular variable. So I want to turn off the constraint so that it can behave more freely. If I want to do that, then I can use the constraint mode, and when I turn it off, it only turns off for that particular variable. So it provides you better control. So generally use one constraint block per one variable unless and until you have a very definitive reason why not to do so. However, the language doesn't prevent you from doing that. It's just a guideline. And the name of the constraint block is also used to override it in the derived class. This we have already seen an example. And due to declarative nature of the constraints, there are certain restrictions, few key ones that I'm calling out over here. Actually, you can use functions within the constraint. So far, I think like we have looked at expressions being used in the constraint, but you can actually write functions that act as the part of the constraint, but they have certain limitations. So we look at one of the limitation in the future slides. And then the operators with side effects such as this plus plus and minus minus, that is increment after usage or increment before usage, or decrement before usage, decrement after usage type of a things that have indirect side effects are not allowed. And Randc variable cannot be used in ordering constraints. There's a concept called solve before, wherein you can specify which constraint should be solved before another constraints because of certain control over how the distribution of the random values needs to take place. You use the solve before. That solve before you can't do it with the Randc. So Randc is cyclic, it is sensitive. There are more limitations associated with it, then we will see them as we go through this session, but this is one of them. And similar to extern task or functions, constraints can also be defined as extern. I myself have not used it. Generally, constraints are not so big that they run over another page, so you need to provide a prototype and then declare them at the bottom. I have not done it, but yeah, the language provides the ability for you to do it. So we have looked at constraint as a overall three-step solution, and we have defined the constraint block. Now in the next few slides, what we will do is we will go deeper into each of the operators that we can utilize within the constraints, and how do they help us generate different type of constraint random stimulus. So that is what we will focus on in the next few slides about the operators. So we'll start off with one of the very useful operators that we will use in the constraints for many problems. So this is the set membership or the inside operator. This operator we have already seen. Now we will look at how does it behave when we use it inside the constraint. So we have a few examples to make sense out of it. So here is the first one. So what we are doing over here is we are saying, so of course it goes without saying that the variable x over here is declared as a rand variable, and our constraint is this rand variable x inside x should be inside these values that we have specified. And let's notice each of these values to figure out how they are allowing us to specify different flavors. So first is, I think we are defining two independent constant values, 3 and 5, and then I have 9 to 15 is a range, okay, and then I have 20 to 24 to 32 is a range, and then here if you notice I have a range which is made up of some variables. So these variables can be again different rand variables, or you can have state variables. It's up to you, but point is you can use variables in the range. So I can say y colon 2 times of the y, right? So some equation for representing the range, and then independently also I can use the individual variables. So now when I say x inside this, it can take any one of them, okay, and then all the values, right, like either single or the value ranges have equal probability of being chosen. So now here I will have 1, 2, 3, 4, 5 and 6, right? So each one of them have equal probability of 1 by 6 of being chosen, and then once this particular range is chosen, within this range one of these particular values, whatever that range is allowing, will be again chosen with the uniform probability. So that is how it works. The second example is, let's look at it. So you can actually combine multiple constraints on the same variable. So I have a constraint block. The name of the constraint block is C2, and I'm saying y inside. I'm specifying a range. So the problem that we are trying to solve is we want to generate odd numbers between 10 to 50. Okay, so we are saying y inside the range we are utilizing, and then y modulo 2, if the remainder is equal to 1, then it's a odd number. Okay, and then if I want to generate, like, let's say random numbers outside the range of 10 to 50, then you can just use this logical negation. So you say y inside the range and then you negate it. So when you do that, it will generate random numbers which are outside this particular range. Okay, that's what it will do. And then you can also like, let's say here this example, what it is trying to show over here is how does the inside ultimately execute. So inside executes as a form of this equation. So if I say a inside b and c, then it means a is equal to b or a is equal to c. So it actually executes as a form of this equation. So most of the constraints, although they might appear procedural in some cases when we go eventually, but they all ultimately get converted to expression and that they get executed. Okay, so that is where, like, for example, many times you will hear the term the constraints are bidirectional. What it means being bidirectional is that it gets converted to expression and the expressions must be satisfied. Okay, and when the expression is satisfied, it imposes sort of rules on the values that each of these variables can take. That is what is it means by being bidirectional. That concept we will discuss a little bit further when we go to the implication. That's where it will become more clear. So yeah, so this is how the set membership operator works. Okay, so as we know, right, as a part of verification, what we are trying to do is we are trying to do the risk reduction, right? And what that means is that at no point we can ensure 100% that the design will be error free. So our goal is that we want to ensure the most critical part of the design has least number of bugs. And in order to do that, whatever the stimulus that we are generating, we want to target the critical area more and more, so that the number of bugs found in the critical area are fewer. And the way we do that is using this construct, not the construct, the operator called dist, which is used inside the constraint construct, right? Within the constraint block, we use the dist operator, and using the dist operator, we can spread out the scenarios. So we will look into it. So we'll look into how this works and how we can use it in one of its use cases, right? What are real life use cases? So distribution essentially guarantees two properties. So one is that it guarantees set membership. That is, you can think that a dist operator is implicitly also a set membership operator. So it is a set membership operator plus something more. Okay, so that's the implicit meaning. Okay, it's not exactly same. I'll tell you why that is so. So I can use dist which guarantees that set membership. So whatever that I have defined in that particular value sets, then your random value will take those values. Plus I can define a monotonic weighting. Okay, so there is a formula, that is why it is monotonic, and I can define those formulas with which the probability would get distributed. And the weights can be specified with any integral expression including value 0. And there are two ways in which you can specify the weights, and we will look into the examples of each one of them. So there is a colon equal to. So when you say colon equal to, it assigns the same weight to all the values in the range. So let's look at an example. So let's say I have this random variable x, and I am saying x distributed, and in this parenthesis I am specifying the values. So I am specifying first as a range, which is 100 to 102 is one range, and I have a value 200, and then I have value 300. Okay, and I am using colon equal to operator on all three elements. So I am saying colon equal to on this range, 1 and then colon, then with the 200 I am saying colon equal to 2, with 300 I am saying colon equal to 5. Okay, so when I do this, what happens is within this range, that is 100 to 102, I have three values, that is I have 100, 101 and 102. Okay, and all three values get a same weight, that is a weight of 1. So overall weighted ratio for this particular dist is that 1 1 1 for these values 100, 101 and 102, and then a distribution the weight of 2 for the value 200, and a distribution weight of 5 for the value 300. So one point that you might want to keep in mind is, now let's say this is 1 plus 1 plus 1, this is 3 plus 2 is 5, and 5 plus 5 is 10. So if I generate 10 samples, can I guarantee that I will be able to see all the values with this particular weight? That is the question. Now with a small sample size, it may or may not happen, but what it guarantees is that when you generate statistically significant number of samples, you will be able to see approximately this particular weight holding up. Okay, so that is what this guarantees. If you use a very small sample size, then there is no guarantee that you will be able to exactly see these weights. Let's look at the second way of specifying weight. So second way is, you can say colon forward slash. So what it does is it divides the weight equally among all the values in the list. So here I am saying 100 to 102, I am saying instead of using colon equal to, I am saying colon forward slash of 1. Okay, so this has more sense when you have the range. Okay, so if you do not have the range, then it doesn't make much difference. So when I do this now among the three values, so I have to distribute them, divide them equally. So what happens is, now the weighted ratio, instead of becoming 1 in the previous case where I was using colon equal to, now it becomes 1 by 3. So there are three values and a weight value of 1. So it gets divided equally. So it becomes 1 by 3, 1 by 3, 1 by 3 for 100, 101 and 102 compared to 1, 1, 1 in the previous case of using colon equal to. And then the remaining two, of course, we are keeping them same. So 200 and 300, they remain 2 and 5. Even if I had done a forward slash, it wouldn't make a difference because it's just a single value. So it will remain same. But when I have a range, it gets divided equally. Okay, so now one other point that we need to take into consideration, as I said, okay, like dist and the set membership, they are not exactly same. Why? Right, so if I have defined a constraint and I have defined a distribution, the both of them are possible. So what I can do is, I can say x inside 0 to 100. Okay, and then I will also define distribution saying that x distribution. Now there are two possibilities. One is, I can only define the distribution for, let's say, values between 10 to 20 and 50 to 60. So I will define the weight for them. The rest of them will remain equiprobable. For this one, I can define a different weights, either reduce them or increase them. Right. So now I have two things. Right. So now the constraint solver will solve the constraint and will also solve the distribution. So that is why you can define both of them. Now if I have a case wherein my inside says I am saying 0 to 100, whereas with the distribution I add one more range. I had 10 20, I had 50 to 60, now I add, let's say, 101 to 110. I add a weight for that. Now the set membership for the distribution cannot be satisfied because in the constraint I have put x inside 0 to 100. So in which case what will happen is, the constraint solver will satisfy only constraints. So when in conflict or when the dist cannot be satisfied, only the constraints takes the priority and the constraint will be satisfied. And only exception to that is the dist weight being 0. Okay, dist weight being 0 acts as a constraint. That is, that particular value should not happen. Okay, so only in that case both of them needs to be satisfied, and if both of them cannot be satisfied, then there results a constraint failure. But and for rest of the values, it will always be, it will satisfy the constraint and it will ignore dist if it cannot satisfy the dist. And the dist cannot be applied on a Randc variable. So where they already have that cyclic way of generating the value, so you cannot apply a distribution on that, because then that violates the ability for Randc to hold on its property of being able to generate it cyclically. Let's look at an use case. So here what we are saying is, So these are the error distributions. This you will be able to see even in the UR test bench, that we have three different type of errors that we can inject, right? So what we are saying is, we are saying that when this particular variable value is 1, the error gets injected. So that value we are keeping it lower compared to the disabled. So normally you will not inject error, and only in the rare fewer cases you will inject the error. So this way you are saying that you are covering error injection, but you are prioritizing the normal operation. So now other thing that you want to note is that the distribution may not remain same throughout the project. During the beginning of your project, you want to focus on the normal operation and you want to focus on the critical areas, and then if you are able to satisfy them, then towards the end of the project, when all the critical items have been met and they have been satisfactory, then you can, and if there is still time, you can change the distribution such that now you start focusing on the next priority areas, right? So you can increase the error injection and then test with the more error injection capability. So initially you focus on normal operation, make sure the normal operation is all okay. If the normal operation itself is not okay, then what's the point of verifying with error injection, right? So that is why you start off with the normal operation, give higher probability to that, give lower probability to error injection, so that still you're able to see few cases, and as the project progresses, if you have more time, then you can include the low probability cases, you can make it high probability, you can make it low probability, and focus on a different area. So that's how the distribution constructs helps you focus the randomization to a specific area of the priority where you are trying to do the risk reduction. Okay, so certain cases you may require that you want to generate your constraint random values, especially when you're talking about multiple values. Those multiple values could be multiple scalar variables or elements of arrays. It can be both of them. So you want basically the group of variables to have unique values, right? You don't want any duplication. So both are two different ways of saying the same thing. You don't want duplication, or you want the unique value. So when you want to do that, you use the operator called unique. Okay, so the unique operator helps you do that. So let's look at two examples. One example with the different scalar values and another example with the array. Okay, so let's say that I have these three variables that I have defined. I have on this line 100, I am defining rand byte, I am defining an unpacked array of bytes containing 5 elements, and I am defining one byte variable, and I'm also defining one more byte variable called excluded. Okay, and now what I'm saying is I'm putting a constraint u and I'm saying unique. Okay, and this is again the your curly braces that I have put in over here, and what I'm saying is unique, and I'm saying b comma a of 2 to 3. So I can do range based addressing for the unpacked array, and then saying comma excluded, the other curly brace is hidden on this particular the box that is coming over here, but it's already there. So I am saying unique and I'm putting this in the curly braces, and then you have to keep making a note that at the end of the expression that you will have a semicolon within the constraint block. So sometimes it might appear slightly different, so just pay attention to that. And then we have the curly braces of the constraint block itself. So we have essentially two pairs of curly braces over here. So same goes for the dist and the inside operator. So you'll have two pairs. Okay, so we saying unique. So now what this means is that, and I am also putting an additional constraint called exclusion, where I am saying excluded value should be equal to 5. So this variable excluded is participating both in unique as well as I have a separate constraint on that. And now when I put this unique, it means that now B and A2 and 3, right? They have to be unique by themselves. That is the first thing, and they cannot also take a value of 5. Okay, so the value of 5 is gone. All right, so now the constraint solver will put this constraint, it will satisfy, and then it will say these variables b2 colon 3 cannot take a value of 5, and among them also they have to take different values. So that's what this particular constraint means. Let's look at one more example. So this is for the array, and the requirement of the problem is such that, so this one you want to pay attention and look at how different array methods are also kind of getting used over here. So we want an integer array of integers, and the size of array should be between 10 and 20, between 10 and 20, between 10 to 20 we want the size, and then we want each element of the array to be of the value 1 to 100. Okay, and then we want the array should not have any duplication. So array should not have any duplicate elements, it should have all unique elements. Okay, so that is what we want. So now what we do is we declare a dynamic array. So we are saying dynamic array of integers, randint payload, right? Payload is the name of our array and it's a dynamic array, and I declare a constraint block C1. Okay, so I have put these curly braces. So I have declared a constraint block, and inside the constraint block now I am using the array methods. So I am saying payload, which is the name of my array, dot size. This is the method. This method tells me what should be the size of my array. So I am saying inside between 10 to 20. This is the first step. So this is my first requirement, that my array size should be between 10 to 20. Okay, so this is the first requirement I have satisfied. The second requirement is that each of the element in that particular array should be within this range 1 to 100. So for that I am using the set membership operator. So I am using this for each loop. The for each loop can be used within the constraints. We will look at this particular construct. It will come in the next slide. Just take it on the face value at this point. So I am saying for each of the values in the particular payload, I am using this index, and I am saying each value should be inside 100, 1 to 100. So that will satisfy the second requirement. The third requirement, which is what applies to the operator that we are currently looking at, which is the unique. So we are saying array should not have any duplication. So I will just say unique, and in that curly braces I'll just pass the payload. So here in the curly braces I was passing different scalar values, but here I am passing the entire array. Okay, so this will make sure that this array that is generated is of the size 10 to 20, and each element in that particular array is between 1 to 100, and then it has the unique values, right? So it will satisfy that, and it will provide you those unique numbers. Okay, let's look at the implication operator. So the implication operator is one of the important operators of the constraint block. So whenever you have a scenario that you want to define a relationship between two variables, that is saying when this particular variable takes certain values, then you want the another variable to take certain set of values in a one way, right? So in those cases you use either you have two options. You can either use an implication operator or you can use a if else. Both are equivalent. The only difference is in if else you have just the structural difference, that when if, then you can provide certain the constraints, and else you can provide certain set of constraints. But the way even the else executes is it executes exactly in a way negation of its implication operator that you have used in if. That's the only way it works. Apart from that, there is no difference. When I say it works in the implication operator or the implication expression, what do I mean by that is that if you remember, in case of operators we had studied this implication operator. So the Boolean equivalent of the implication operator is, so if I have x implication y, what that means is, it just means the overall expression must be true. That is not of x, or the negation of x expression, and then logical operator or, and then y. So this overall expression must be true, and then which means that the x implied y has become true. That's what it means. Okay, so when we look at an example, it will become more clear, but formally let's define it. So what I'm saying is expression implication operator constraint set. What this means is that if this expression is true, then the random numbers generated are constrained by the constraint, and if this expression is false, then the random numbers generated are unconstrained. That's what it means. So let's take an example. Pay attention over here. This is a slightly confusing concept. So I have two 4-bit vectors over here. So I have said rand bit 3:0 a comma b. So which means both a and b are 4 bits. So when they are both 4 bits, they can totally take 8 bits worth of value. So in the absence of, let's say, I don't even have this implication operator constraint, that is constraint C, constraint block C, and I'm saying if a is equal to 0, if a equal to 0 implies b must be equal to 1. So this constraint I have, let's say I have not defined this constraint, and I have only line 126 in the class, and I randomize that particular class. The total number of values that are possible are 2 raised to 8, because the combinations I'm talking about, right? So the combination of A and B that are possible are 2 raised to 8, because each one of them is 4 bits, right? So 2 4 bits, we have 8 bits, so 2 raised to 8 is 256. So every probability of every combination that is taking place, which includes A equal to 0 and B equal to 1 as well, that combination will include A equal to 0 and B equal to 1, is 1 divided by 256. Now let me introduce this implication constraint, that is the line 127. I'll say this constraint block, constraint C, A equal to 0, B equal to 1. Now let's understand how this affects the overall probability. So when I say this, right, what this means is when A is equal to 0, B cannot be equal to 2, B cannot even be equal to 0, right? So B cannot be 3, so on and so forth. B cannot be 15. So when A is equal to 0, B can only be value of 1, so which eliminates these 15 combinations, right? So if I eliminate these 15 combinations, which means 1 divided by 256 minus 15, which means 1 divided by 241 is the probability that A will be equal to 0 and B will be equal to 1. Okay, now the question is, and sometime you will end up hearing the statement like implication operator is bidirectional. So does that mean when B is equal to 1, A must be equal to 0? The answer is no. Okay, and why is that no? We'll understand. So when B is equal to 1, A can be equal to 2. How is that possible? The reason why that is possible is we have A and B are two different variables. Okay, and constraint solver can solve for B before A. It's possible. So let's say I solved B is equal to 1 and then I solved A is equal to 2. It's possible. So now why is that possible and why is that correct? For that we need to look into this particular logical expression. Now let's say I take a value that B is equal to 1. So B is equal to 1, meaning what happened? The value of B is equal to 1. So this particular B equal to 1 will, the expression is evaluating, this particular constraint set is evaluating true. So this Y became true here. Okay. Now once this becomes true, irrespective of whether the other expression becomes true or false, the overall expression will still be true. What is the value of A? Value of A is 2. And is 2 equal to 0? No. So that is false. So A equal to 0 as an expression has become false when the value of A is equal to 2. But if I substitute that false over here, because X, which is A equal to 0, has become false because the value of A is equal to 2. Now that has become, when I negate it, it will become true. It doesn't matter. It has true logical operator of OR, and B is equal to 1, which is again true. True or true will remain true. Now A can be also equal to 0. So if I insert 0 over here, 0 equal to 0, true. If I bring that true over here and put it over here, it's a negation of true, it will become false. False logical OR of Y. Why? I said B equal to 1. So 1 equal to 1 is true. So false or true will be still true. So I have to satisfy this expression, and that bidirectional means this will have some effect on this, or this will have some effect on this. That is all that it means. Apart from that, it is not, it doesn't imply that when B is equal to 1, the A must become equal to 0. When B is equal to 1, A can be any value. A can be 1, 2, 3, 4. That is why it gets included in this 1 divided by 241. But what this whole expression means is in a way it is one way. That is when if you want to just understand it in a layman type of a terms, that when A is equal to 0, B must be equal to 1. But when B is equal to 1 doesn't imply A is equal to 0. Okay. So, and how to understand that, you should always come back to this logical Boolean equivalent of the implication operator. What is that? So ultimately the constraint solver is expected to satisfy this particular expression and nothing else. Okay, so let's take at this is the example that we have seen in the previous case as well. So we defined one more variable, and then depending on the value of that variable we had provided these implications, right? In this case also, let's say now here we had defined the A type to take these values low, mid and high, and let's say I don't have these constraints, let's say on the line number 40 and 41, that is mid and high, I comment that out, and I have only this particular implication operator, that is a type equal to low implies address must be between 0 to 15. And with this constraint, if I randomize the class, okay, this is one of the value that it has taken. So where the address is 3 and a type is mid, this is possible, okay, because ultimately it has to satisfy this particular expression. Got it, right? So because when you look at address as 3 and a type as mid, so here this a type of mid has become false, right? Because when I put mid over here, mid is equal to low will become false, and that false will become true over here, right? And then a type is equal to this again has become true. So true or true has become true. Okay, so that is where when you have multiple variables and you are establishing the relationship using the implication operator, you remember that it only goes this way from left to right. It doesn't imply that if the address gets solved first, then it doesn't imply this to hold true. If you really want the order to be maintained, then we will see that we have one more way to impose the ordering, that I always want the a type to be solved before I solve the next one, address. So you can put a solve before type of a construct if you want to impose that relationship. But when such a relationship is not defined, the constraint solver can solve these two variables independently and must ensure that this Boolean expression equivalent that I have defined must hold true for the implication operator. But in just a layman's view, if you want to remember without worrying about the theory that I explained, always remember that it goes from left to right, not from right to left. Okay, so if else is actually another form of an implication type of a constraint. The formal definition looks something like this. So you have if expression, and then you can specify set of constraints, and then the else part is optional. So you can say else another set of constraints, and constraint set represents sort of any valid constraints, or like unnamed constraint set. You cannot give a name to it, but you can actually group multiple set of constraints within each of these block, and if this expression is true, then the constraints in the first constraint set shall be satisfied. Otherwise, constraints in the optional else constraint set shall be satisfied. You can use else, and you can do if, so that way you can continue a series of if else if as well in the if else constraints. And as we have discussed, if else and implications are equivalent, and hence it's not like a procedural execution, but it's still what do I mean by it's not a procedural execution is it still evaluates the expression, right? So we have seen the expression for implication, right? So if I look at mode equal to little and then length less than 10, what that means is in terms of implication it would have meant mode equal to little implies length less than 10. Okay, now if assuming that, let's say if the else if was not there, and if it was just a else and we were saying length greater than 10, then the else portion of the if would have been like not of this particular implication, right? That is, see, we know that implication is not of first expression and a logical or and then the second expression, then it would be a not of that. Okay, that is what would be used for representing else if there wasn't any condition. But any if else structure can also be represented using implication. For example, this constraint that I have over here, I can represent it in the form of an implication, two implication statements using using this particular syntax, right? So I can say mode equal to big, and then I can say that implies length greater than 100. So this way both of them are equivalent, and sometimes this is more convenient, and sometimes if it is the implication is more convenient. So depending on what makes more sense to represent, then you can choose that form of a constraint, but both provide you the same or similar functionality. Okay, so whenever you have a certain set of arrays, you can use this iterative constraints approach to loop over each element of the array and add constraints on each of the elements. Okay, so the formal syntax looks something like this. You say for each, then the array identifier, then you utilize a loop variable, and then you define the set of constraints. And these set of constraints apply to each of the element of the array that we have put it in the for each. So any array can be utilized, any type of array can be utilized. It could be a fixed size array, it could be a dynamic array, or it could be an associative array or a queue. Any type of these arrays are utilized. Typically, I think like dynamic and the queues find a lot of application because they allow you the dynamic scaling of the size, which is very helpful. So you randomize a packet, and then let's say if you are using the dynamic array or the queue for representing the payload, then you can randomize the size and then randomize the size of queue or a dynamic array to hold the random data elements that needs to be created for a particular packet. So that way, I think the dynamic arrays or queues are very helpful. And then for each element of those dynamic arrays or queues, you can use this for each to implement the actual constraints. And the type of each loop variable, that is this particular loop variable, will be implicitly declared, and it will be consistent with the type of array index. Generally, the fixed size, dynamic, or the queues, they use integral index. Only the associative array can use a different types, but the loop variable type that gets implicitly declared will match the type of the array index. Okay. And like as we have seen in case of the regular multi-dimensional arrays as a part of our previous session, if you leave an empty loop variable, it indicates no iteration over that particular dimension. So that particular concept remains same. And the size method of dynamic array or queues can be used, as we talked about briefly, to constrain the size of array. This is a very useful and important feature. And when we do that, typically what we are doing, we are constraining the size of array, and then we are constraining something for each element of the array. So in those cases, first the size gets solved implicitly. It's implicit, you don't have to order it. So first it will figure out the size, it will solve the size constraint, and then it will go over each of the elements of the array. I mean, that only makes sense, but that's how it works as well. And the way you have to look at it when we think of any constraints, don't think of these for each or if as a sort of procedural block. They look similar to that, but they don't work similar to that. So what happens is, when you have for each, once you have solved for the size, think of it like before the solver solves for each of the element of the array, it gets unrolled. Unrolled meaning if I have, like let's say in this case I have array, I'm solving it for size of 4, right? So there will be 4 equations that will get created. So for each one of them, so this will really become 0 plus 1 should be greater than 0, and then like that would become like 1 greater than 0 and 2 greater than 1, and then 3 greater than 2, and so on and so forth, right? So all those steps will get unrolled and they will become individual steps. So this one line that's on the line 144 will become actually the 4 statements over here, because I am constraining it to size of 4. Okay, so similarly also if you have n, it will become n lines, and that is what the series of equations that the constraint solver will solve. It will solve all of those equations to make sure that everyone gets satisfied. Whatever the relationship exists between them, it will satisfy, and it will satisfy meaning it will pick the random values that will satisfy all of those equations. That is what it will do. It will unroll and pick up the solution, and this will not execute like a procedural way that one after another. It won't work. The main point that you need to understand is that if we solve it like, let's say if I solve one after another, I solve the previous one, and then when I go to next step, if I find that okay, this particular, if I do it this way, then I cannot pick the value that I have already picked, then you can't just go back, right? So that is why what happens, it unrolls and parallelly solves all of them together, such that whatever the values that you are picking is ultimately satisfying all the equations at the same time. That is the main fundamental, right? So I hope that that concept is clear. Since we need to satisfy all of them at once, we can't just do one by one. We have to do all of them together. That is why unrolling of loop happens when we solve it in the context of the constraint. So let's look at one of the example of how the for each works. So here what we have done is we have declared 2 queues. We are solving the same problem. In one case we are just using the if, and another case we are using the implication operator to show that again like they are equivalent, right? So that point we are just driving it again. So we are first solving for the array size, okay, and then we are saying it should be 4. It can be any range. For simplicity of explanation, I picked 4. I just wanted to tell you about those unrolling aspect, but it can be range or it can be some discrete values as well. So this inside anyway set membership we have seen. So all possible things that we have shown with the set membership could be used over here, and then you say for each of the elements of that particular array, and if the I less than array q dot size -1, so we are ensuring that we are going till the last but one element, and then we are ensuring that each successive element is greater than the previous element, so that sort of the random numbers are generated in an ascending order. That is what this particular constraint will be able to accomplish. And then we have an additional constraint saying that then each of the elements should be in the range of 1 to 100. So it has to pick a number between 1 to 100, and then it will have 4 elements, and each of those elements, whatever the random numbers that it has picked between 1 to 100, will be arranged in the ascending order. Now this if condition that I have on the line 144, 145 and 146, where I have an expression and then I have a constraint set, I can replace it with the implication operator saying on this line 154, rest of this thing, whole thing remains same. So I'm saying I less than array size -1 implies array of I plus 1 greater than array of I, right? I can just put this one, and then the next one remains same, array of I inside 1 to 100 remains same. So both of these ways of doing things are essentially accomplishing the same thing. Okay, so you can use the iterative constraint wherever you are constraining the arrays, each element of array. If you want to put constraints on each element of array, then you can use the foreach construct. Okay, let's look at one more practical example for using the iteration. So in the previous case, we were using a simple one-dimensional queue. So here we'll try out the multi-dimensional, which is also another popular example. Generally 2D at least is a popular use cases. Just for the completeness, I am showing one more area wherein like I have a 3-dimensional array, and it's an unpacked arrays. Typically, as we have discussed in Testbenches, we tend to use unpacked arrays because it allows the allows us the flexibility to use any data type, which is very important for building the Testbenches. So we are using unpacked array, and I can do for each of a within this square brackets, I can specify the dimensions that I want to iterate, and then I can put in whatever the constraints that I want to put it in. And then if you want to skip a particular dimension, then you can just use an empty, you can just leave that particular thing empty, and that particular dimension gets left out, and you get to constrain the rest of the dimension. So that is another way that you can do it in some use cases. But let's look at one practical example. So this is one of the popular problems that you want to generate some matrix type of a random data. So scalar matrix is a flavor of a diagonal matrix problem. So scalar matrix means that your diagonal elements are of the same value, and the rest of the elements in the matrix will be 0. Okay, so the scalar matrix can be of these two flavors. One, it moves from the it moves the starting dimension is on the like a00, a11 and a12. These are the dimensions that could be used, or it could be using in the other way around, that is it starts from the right side corner, and then it could use b0 to b11 and b20. So either of them could be utilized. And if we do that, then how to go about solving this type of a problem? So the problem definition over here is I want to randomly generate a scalar matrix either of this form or of this form, right? The one that starts from the top left corner, or the one that starts from the top right corner. One of them I want to pick and solve them. So let's see, we will look at how to do it for both of them. This part of the code that I'm showing on the left side is common. Only the one that on the right hand side becomes specific depending on the type of scalar matrix that you want to generate. So first what we are going to do is we are going to declare a dynamic array, two-dimensional dynamic array. And of course here we are picking size I and size j for 2 dimensions, but only one would have also been sufficient because anyway we want both of them to be of both the sides to be equal anyway. But anyway, so just shows you how to do it flexible way. Then we have one more rand int unsigned x, and this x value is the common value that we want to keep. Okay, so those are the three properties that we are declaring. Now let's look at the constraints. So in the first time, what we are trying to do is we are trying to say the dimension of this type of matrix that we want to generate should be greater than 2 and less than 7. Okay, so first we are constraining the dimension, and we are saying size j equal to size I. As I said, we could have used the common variable as well. So anyway, so we are first generating the dimensions of the matrix, and once we have generated the dimension, as you can see here, both the dimensions are dynamic array. So which means that both of them have to be created or allocated. So when you constrain the size, they automatically gets allocated. You don't have to really do equal to new in a way that we did it in the procedural context. You don't have to do that. When you constrain the size of a particular array in the constraints, that particular dynamic array gets allocated automatically. Okay, so what we are going to do, so first we are going to say the first dimension. So we are going to say array and size equal to size of I. So we are allocating the first dimension. Okay, so we created first dimension, and so many elements got created, and each of those elements now has to contain again multiple elements in it. Okay, so each of this is actually this one dimension got allocated, and even after the one dimension got allocated, the second dimension is still an array. That is what is happening. Okay, so now what I am doing, I am going to the second dimension. So I am going to say array of size of I, and then I am allocating the second dimension. I am saying array of size of I dot size, right? So I am going through each of element of this particular array, and I am now initializing the second dimension, and I am saying that is equal to size of j. Okay, so we created first 1D dynamic array, then when we created 1D dynamic array, each element was again a dynamic array, because that's what the two-dimensional dynamic array means, right? And then we went into each of those dimensions, which but themselves are again dynamic array, and we constrained the size of them. Okay, so we constrained the size of them. So now once this particular iteration for each loop completes, then we have allocated the 2D array. So 2D array means we have to allocate it, because it's 2 dimensions, you have to allocate it twice. Okay, first create the first dimension of dynamic arrays, and then go into each of the dimensions and allocate the dynamic array present in each of the dimensions. So that's what we did over here in this line 188. So once we have done, now our 2D dynamic array is ready. Now what we want to do is we want to constrain the values. That is what we want to do. If we don't constrain the values, then those will be some random numbers. So now we want them to be specific values. That is, in this case, we want a scalar matrix starting on the top left corner. So what we are going to do, we are going to define this constraint block C2. Okay, and we will complete this curly braces, and then we are saying for each of, now if you see, we are iterating over both the dimensions, similar to what we saw here. So we are iterating over both the dimensions, and whenever I is equal to j, because here if you see the indices, right, so it is 0 0 1 1 and 2 2. So whenever I is equal to j, we are saying array of I comma j is equal to x. That is the fixed random number that we have generated. We want that particular value to be taken by this diagonal elements, and else we want to say array of I comma j equal to 0, which will be this rest of the elements. So that is how you do it. So this logic that I have marked I equal to j, you might want to remember, this is a logic for accessing the diagonal elements when you want to access it from left to right. Now other way around, if I want to do it from right to left, right, I start want to top right corner, I want to come up to the left side, then the way how the constraint is going to work, we can look at it over here. So we are saying again constraint block C1, and we are again going through both the dimensions. So note over here, one thing I want you guys to look at when we declare the for each loop, within the one square brackets we are doing the comma separated list of the dimensions. So that is something, it's not, when we access it as this way, right? That is, we have whatever the number of dimensions, that many pairs of square brackets we utilize when we want to access the elements. But when we are iterating over multi-dimensional arrays, we use only one pair of square brackets, and within that we do the comma separated list of indices. So that is one factor I just want you guys to notice. So we say for each of array of, again within single pair we are saying I comma j, and then the logic that we use over here is if I plus j is equal to size of I minus 1. Okay, so what does that mean? So if I add 0 plus 2, then it is size of I minus 1. So size of I will be 3 in this case, and if I add 0 plus 2, it will be less than 3, right? Sorry, it will be equal to size of I minus 1, it will be equal to 2. And if I again add over here I plus j, which is 1 plus 1, it will be 2, again size of I minus 1 equal to that. If I add 2 plus 0, it's 2, again that's equal to size of I minus 1, which is 3 minus 1 equal to 2. So in all this right to left type of a cases, if I add indices, the sum of the indices will be less than the size of the dimension minus 1. So that's what we are trying to say. And if that is the case, if it is matching, then it means these are the right to left diagonal elements that I'm accessing. I will say array of, I will use now two pair of square brackets because I'm now accessing the element of array. I will say I comma j equal to, double equal to x. So whatever the x value, that I can add an additional constraint for it to take some value within a range, and then is equal to x, else then array of I comma j is equal to 0, which is these elements on the top and the bottom corner, they become zeros, right? So this way you can solve for a scalar matrix problem using the two-dimensional arrays, and you just have to remember this particular logic a bit so that you can solve these problems easily. Let's look at another flavor of iterator called with. Okay, it also does the iterations. So let's define a problem and then we look at how this iterator helps. We have defined this rand and a dynamic array of 8 bits. So it's a dynamic array of 8 bits, and we are putting in a constraint on the size of this particular dynamic array, and we are saying a dot size should be equal to 5. So this the array, now we have constrained it, it will contain 5 elements and each of the element will be a 8-bit vector. Okay, now I'm putting another constraint block C2. I'm saying a dot sum, which is the array reduction method, should be, let's say that I have not put this width, and I'm saying it should be less than 1000. Now what happens is, whenever you use any array reduction methods, right, array reduction method, it returns the final result as a same data type as whatever the data type of each element of the array. So in this case, each element of the array is bit 7:0, and hence a sum would also try to fit it into that particular number. But as we know, the maximum value will be 255, and of course if I am returning the sum in a 8-bit number, it will cause a overflow, right? It can't hold 1000, right? So in order to hold 1000, you need at least 10 bits, right? But whereas you are having only the 8 bits, so obviously it's going to cause the overflow. So now what you want to do is, you want to cast each of the element to a data type that can hold the final sum that you are trying to target. So in this case, what we are saying, a dot sum, we are using the with form of an iterator and saying with, and then we are doing a static casting. We are saying int cast each element of this particular array to be of the type int. That's what we are saying when we say a dot sum with int static cast for an item. Okay, so item is a built-in variable. You can use any name. Here I have just used it as an item. It could be any name that gets implicitly allocated, and it refers to sort of, you are going through each one of them, and like it's saying like whatever a of I. Okay, so it's referring to each element that's present in the array, and you are giving an identifier name for it, and it is equivalent to whatever I have pointed out on this line number 214, that it is unrolled. So I'm saying int of static casted int of a0 plus static casted int of a1 and so on and so forth up to static casted int of a4. So all the elements are casted to int, and hence the return sum will also be of the type int, and int, as you know, it holds up to 32-bit, so there is no overflow problem. So this way you can solve the possibility of overflow using the with iterator. Okay, sometimes what happens is you are either building uh, a group of, like, a relationship between certain set of objects, or you have a complex problem that you want to distribute across multiple objects and then kind of link them together. So when you have such a type of a implementation, then what happens is you have one object and then you have a series of low level objects. You instantiate those low level objects in the top level object, and you utilize the values from the low level objects to constrain some of the variables in the high level object, right? So in this way you have interlinking of interlinking of constraints by using the values from different objects. So when you do implement it in such a pattern, it's called as a global constraint or a hierarchical constraint. So like a formal definition is a constraint expression involving random variables from other objects, right? It's called as a global constraint. And when you declare when you create a global constraint, so what ends up happening is whatever the low level objects that you are relying on, those themselves become like a rand variables within this top level object. And when that happens, then when you call the randomize on the top level object, all the rand variables across this hierarchy, right, and all the constraints across this hierarchy are solved simultaneously to satisfy to pick values such that it satisfies all the constraints at all the hierarchies, right? So now that is because of this interlinked usage of the variables from the low level objects into the high level objects. So let's look at an example to get the clarity. So here what we are doing is we are sort of building a linked list and then providing constraints for the values across the nodes. Okay, so that is the example that we are taking. So we have a class A, you can think of it as a node in the linked list, and we have one random 8-bit vector which is the node value. And then what we are doing is we are extending the class B from the A. So think of it like the B is also a node, and so it will get the value, and we want to now put the constraints on this value for the current node, such that the current node value should be greater than or equal to the node on the left hand side, and the node on the right hand side should be greater than the current value. So that is what we want to do it over here. So now if you look at it, what we have done is we have declared a rand of the type object, right? So it is a handle we are declaring, rand a left, and the a is of the class data type, and then we are declaring one more node right, which is also of a class data type of the type A, right? And then we are using the variables that are present, variables or properties that are present in that rand class object within the constraints. Okay, so that is what we are doing over here. We are involving the random variables from other objects are called as global constraints. So this is what is the global constraint. And note that when you do this, like in the dynamic arrays, we called out that because we constrained the size, the array got allocated automatically, and just because we have declared a rand handle of a class data type, the object doesn't get created automatically. So you still, in the constructor, you still have to call the constructor for the handles that you have created in order for the objects to get created. And thus when in the top level program, when we say class B and we create a handle of the class B type, and we say the new, when we construct the top level object, automatically the objects that are used within the rand objects which are used within this B also get allocated, and thereon only you need to call the randomize. If you don't do that, then you will experience like a null handle reference, because these would just be handle, they won't contain any object. And then when you use left.v, it will be a null object reference, and hence your constraint will fail. So you need to allocate the objects and then call the randomize when you are doing the global constraints. Okay, so as we have seen right in the previous examples, also while especially while discussing the implication operator, that the constraint solver will try to create the random values such that it gives an uniform value distribution, right? And sometimes what happens is, as we saw even with the dist type of a construct, that you want certain combination to occur more frequently. Okay, so one is, of course, you have the dist which provides you certain level of control, but there is another way that you can add additional control using an approach called like a solve before. And so how to do that, let's look at it. And please note that when you add the change in the ordering of the constraint set, it doesn't alter the overall solution space. That is, whatever the values that needs to get generated that is possible will all get generated, but only it alters their probability of occurrence. Okay, so solve before, and it does not change the solution space. So because of that, just by adding solve before, you cannot cause the solver to fail. And Randc variables, as we have seen even with the like the dist operator, we cannot use them because they already have like a fixed more stringent constraint that they have to be cyclic. And then the constraint block, a same constraint block can contain both the regular value constraints as well as ordering constraints. However, in the example we have separated them out, but you can put both of them in the same constraint block as well. There's no problem. So let's understand how the usage works with the example. So I have a random bit vector of 32 bits of the type D. Okay, so now if I do not put this line 230, 231, and if I just had in a class line 229 and I randomized it, then a 32-bit variable can take 2 raised to 32, right? Approximately up to 4 gig values are allowed, and then probability of each value will be 1 divided by 4 gig. And let's say that in that case, if the value 0 is something that is special, then the probability of that particular value 0 happening is same as like 1 divided by 4 gig, so it goes very low. Now if I want that particular value to have a higher probability of occurrence, then one thing I can do is I'll add one more variable called rand bit s. Okay, it's similar to the concept that we had done it with the address type variable, where we had done the division to be like low, mid and high. Same way we are doing, like adding one more variable bit s, and we are saying adding additional constraint on this line 230, saying that when the s is set, it implies that d must be equal to 0, and we are putting additional constraint for the ordering using the solve before. We are saying solve s before d, so it will be forced to solve the s, right? And because of that, the s will take a value 0 or 1. Okay, and if it takes a value of 0, the d can take any unconstrained value, but if s takes a value 1, then d is equal to 0. But s taking a value of 0 or 1 has a 50-50% probability, and hence the value 0 will now get a 50% probability, right, compared to other values, other whatever, like 4 gig minus 1 values. Compared to them, it's going to get the it's not going to get the 4, it's going to get the half of that probability, and hence the probability of occurrence has increased. So sometimes it might be harder to specify certain things using the dist, and in such cases you can use this solve before approach to control the probability of occurrence. And most of the times constraint solver resolves the dependencies, but if in some cases it is you want to enforce a certain dependency to make the solution in a way that you want it, then you can order them and get the solution that you want. So, okay, functions actually can be used within the constraints. I know when you look at it first, it looks very attractive that you can use functions within the constraints, and hence you can model very more complex functionality. It is true to an extent, like if you require some sort of a temporary state or unbounded loops, then it's kind of hard to put all of that in a single expression. So in those cases, you can use the function, but it comes with lot of restrictions, Like for example, the functions have to be automatic. It cannot take any ref variables. You cannot use any of the class properties within the function, and you cannot use constraint mode, which we'll talk about what is a constraint mode, which helps you to turn on or off a particular constraint. You cannot use them in the functions. And the most important factor that affects when you use a function is the overall solution space gets divided into half. That is, what happens is whatever inputs to the functions that needs to be randomized, they are solved first, and then you send it, and then a function gets called, and whatever the output that you get from the function, you get that, and that output acts as a state, and then you solve the remaining variable. So this way it is solved in a two different parts. So what that means is, when I say it's solved in two different parts, is that when you return the value from a function, it becomes a state. So that's an important point to understand, that if that particular state cannot satisfy the next set of constraints which are based on the state that's returned from your function, then the first thing is the solver will fail. So there is no going back again. So if, because now the state that is returned by a function is not satisfying the next set of constraints, it won't go back to the original initial input variables and resolve them again and again call the function. So that iteration is not going to happen. Okay, so if it cannot satisfy, it just fails. Okay, so if you want to truly have the power wherein all the constraints are solved simultaneously and you arrive at a valid, a legal solution space, then you should try to avoid using the functions. But anyway, let's look at an example to understand how it works. What we have done is, we have one 32-bit mask, and we want to pick one index variable which is randomly selecting the position where the mask is set. So what we are doing is, we are ensuring that we are generating this random 32-bit mask, and we are saying mask should not be equal to 0. So it's a non-zero mask value that gets generated, and then we are saying the mask index or the select mask index must be inside, and we are calling a function here called getIndex, and we are passing this random variable mask over here. So this whole thing gets solved in two stages. First, this non-zero mask gets solved. We generate a non-zero value for the mask. We send it to this function getIndex, and this getIndex gets this input mask and goes through each of the values. So this for each, okay, is different. This for each executes in the procedural context, whereas when I directly use a for each in the constraint, it gets unrolled and each of those values are solved simultaneously. But when you call the function, and whatever the for each that I am using over here, this for each doesn't get unrolled. It so gets solved in a procedural context. So, and you can use all constructs, whatever procedure, like for example, you could use jump statements if it is required. So what I'm doing for each of mask of I, if mask of I, if that particular bit position is set, then the corresponding index I am pushing it into the queue, right? Since this is returning a queue of int, automatically the getIndex implicit variable of the type return gets created within the function. So I'm saying getIndex.pushback of I, and at the end I'm returning that. So now whatever the bit positions where the mask vector was set, those indexes I have it in a queue, and that queue I have returned, and I am now selecting randomly this particular int unsigned select mask index from those positions. So if I had 4-bit positions, let's say 31, 16, 8 and 12 were set, those indexes will be returned and I'll pick one of them. It could be 12, for example, right? So that is what is happening. So here we do not have additional complex constraints, but let's say if we had an additional constraint saying that select mask index should be greater than 20 or something like that, and then it so happens that the mask got randomized such that those positions were not set, then the overall constraint will fail. It will not go back and solve it again. So that is the problem with the usage of the functions, which you need to be aware. So when you solve constraints, you have two types of variables that are involved in solving the constraint. So one is that you are actually using a rand variable, and then second is there could be additional helper variables that could be helping you solve that particular constraints, and those helper variables are generally are of non-rand type, and those variables are called as state variables. Okay, so now the state variables used in the object when you are doing the process of randomizations, they get evaluated before their usage in the constraints to make sure that they have the proper right values. Okay, and we have to make sure that those state variables have the right value so that the constraints don't fail. And some of the cases where the invalid values in the state variables can lead to failures are like if you are using an object within a class. If you are using an object variable and you're trying to access the object variable, like as we saw even in the previous case of global constraints, and if that object handle doesn't have a is not pointing to a valid object, then that particular constraint can fail by the null reference access, right? Or if you are accessing arrays and if you access indices that are out of bounds, then that also can cause the failures in the constraints. And to prevent this, what we do is we add guards. So guards are the additional validation statements on the state variables before you use them in the constraints, and these guards can be created using both implication or if else. As we have seen, both of them are equivalent. So let's look at a few examples. So here this is a class wherein I am using a config object and I am using the config object's variables to constrain a property that is declared in this particular class. So I have declared a randint a and I want a to be greater than the min value that's present in the config object and less than the max value that's present within the config object. And I have declared the handle of a test config called config o. Now if this config o happens to be a null object for some reason, that is before either in this constructor or after the object is constructed directly by referencing a public handle, the objects could be assigned. So if that is not done and if this happens to be a null, then this constraint block C2 will fail. In order to prevent that, what we can do is we can say if config object is not equal to null, and only when then it is not equal to null we are enabling this particular constraint. If not, then the a will take any random value. It won't lead to a constraint failure. Okay, so that is what you can do with the help of the constraint guards. And the second thing is that even when you are accessing the indices, for example, here we have a dynamic array of 5 bits, and then we are saying a of size should be in the range of 8 to 10. In the constraint block C2, when we are doing for each of a of I, we are putting the guard called I greater than 0. So only when the index value is greater than 0, then we are accessing a of I minus 1. Because we are accessing a of I minus 1, if we do not have the guard, then what can happen is the indices can become negative, and the negative indices values can also lead to the constraint failures. So this way you can use the constraint guards either using the implication operator or using the if to validate the state variables before you use them for the randomization. So we have certain use cases wherein what happens is we have, let's say I'm passing a particular value for a specific value to a randomized variable from the command line. You know the command line, right? We run a test and then when we are running the test, I can pass a particular value and that I can extract within the test using value plus arg, and then using the inline constraints. Now I want to send this particular value to a random variable within a class, and then what happens is that there are cases that I might not want to pass this, and there are cases that I might want to pass a specific value that might be in the range that I have already specified. Like I might have specified a range constraint within the class. That could be in that range. It could be out of that particular range, or I might not even pass a value. If I pass a value, then it has to take that specific value. So I have these requirements. Now now what I need is I need some default constraints which to take effect. If I'm not passing any value, it should take the value from that particular range, and if I pass a particular value, it should be that specific value only. Now now it's very simple. I can put a regular constraint, and then when I'm randomizing with, I can take a specific value. So let's say I'm randomizing between 1 to 10, and then I'm passing via command line argument a value of 8. then when I'm saying randomize with, okay, whatever the value that I've gotten from the command line, everything is fine. But if I want to pass, like say it's an error injection type of a scenario, I want to pass a value of 12. My default constraint is taking a value of 1 to 10, but I want to pass a value of 12 for certain error injection scenario. Now when I say inline constraint of equal to 12, as we know, inline constraints are additive. Additive meaning whatever is the existing constraint within the class, along with that the inline constraints adds the additional constraint. And now this additional constraint where I want a specific value of 12 is in conflict with the default constraint that I have specified, wherein the range of values are between 1 to 10, and hence the constraint solver will fail. Okay, so now what is the solution for this type of problem? The solution is using the soft constraints. Okay, so soft constraints are the constraints that can be overridden and overridden in a way such that whenever we have like additive constraints, when multiple constraints are participating, and if the soft constraints cannot be satisfied, then the solver will ignore them. That is the idea of soft constraints, like a dist. For example, we know that if the dist cannot, between the dist and the regular constraint will be prioritized over the dist. A similar way, a soft constraint will be deprioritized over the hard constraint. So far whatever constraints we have seen are all hard constraints, right? And when the hard constraints are not satisfied, it results in failure in randomization. Whereas soft constraints, on the other hand, when they cannot be satisfied, they just get discarded. Okay, and if a call to randomize only involves a soft constraints, then it can never fail. Okay, that is because if they can't be satisfied, they just get discarded. And as we talked about, they are often used to specify default values and distribution for the random variables. And in the absence of soft constraints, the constraints as we talked about, we had to then override it. That is one more solution, that we could have created one more derived object, and we could have used the same constraint name, and we could have overridden with the value that we had passed from the command line. That object, that type of an approach always exists. Or we could have turned off using the constraint mode and then assigned that value. That's also another solution. But all these solutions require extra work. I have to create an extra object, or if I'm turning off the constraint mode, then I might have to turn it on again, because the same object might be getting randomized in the future. So for all those, if you have a default value type of a constraint that you need to specify, which can be overridden with inline constraints, then soft constraint is a better approach. And also the soft constraints provide a much finer granular control, that within a constraint block, whatever the expression that you are defining, because we can define multiple constraints using expressions within a constraint block, and a particular expression you can make it as soft. It doesn't have to be entire constraint block. You have only one expression, you can make it as soft. Let's look at an example to understand. Let's say I have this class A, and I am declaring a value, a random integer value x, and I am putting one constraint, and I am within that constraint block I am defining one soft constraint on the expression, and that expression says that soft x equal to 10. So I am expecting that whenever this class is randomized, I want it to take the value of 10. That is what I want. Okay, now I am creating an object of new, and I am calling object.randomize with, I am specifying an inline constraint saying x should be inside 0 to 12. Okay, so now what happens here? The soft constraint does not cause any conflict, right? This with inline constraint is a hard constraint, and it's an additive hard constraint, right? But it's not conflicting, because I am specifying a range of 12 and then I am saying my soft constraint as 10. So when you do this type of a randomization, you will always see the result of randomization as 10. You will not see other values, because what's happening is the your constraint solver is honoring the soft constraint, because soft constraint is not conflicting with the inline constraint. Okay, so it is honoring, so it will always get the value of 10. But let's say if we take another example and we say same object of the type A, and I'm saying randomize with x inside 5 to 9. Now this range is in conflict with the soft constraint, which wants the value of 10, which is definitely out of this range. Now what happens is that the solver turns off this particular soft constraint, and then it will solve only the hard constraint, and hence here you will see the value of x being generated between 5 to 9. Okay, so this is how the soft constraint works. So when you have hard constraint and when you have soft constraints, and if the soft constraint cannot be satisfied, then it is ignored by the solver and typically used for specifying the default values. Soft constraints can be disabled using the disable soft construct. Now, when you hear this, a question might come in your mind that why do I need to turn it off? Anyway, when you have hard constraints, if the soft constraint is not getting satisfied, it will anyway get ignored, right? So why do I really need to disable it? So let's take a look at an example that will make it more clear. So we have a class M over here and we have randint x, and we have put this constraint block A where it says x should be greater than 2 and x should be less than 10, right? And as we have specified in the previous slide as well, the soft constraint is at the level of expression and not at the level of the complete constraint block. So with this soft constraint, what will happen is whenever I randomize the class M, any number between 3 to 9 will get generated. So I have now a new object and I'm calling object.randomize with, and I'm creating an additional inline constraint saying that x inside 0 to 20. Now what this means is that I want to now generate numbers between 0 to 20, but as I see that 3 to 9 is a part of 0 to 20, so your constraint solver will respect or honor the soft constraint and it will generate only numbers between 3 to 9. But your requirement is that you want to expand the range beyond what has been specified by the soft constraint. Okay, so the key point is the soft constraint restricts the variable values to a range and the test level wants to expand this range. So this is a requirement. When you have this requirement, then what you need to do is you need to use this disable soft x, the name of the variable on which the soft constraint was applied. You can say disable soft constraint on the variable x, and then you say x inside 0 to 20. Now your x will take values between 0 to 20. So this way, whenever you have a requirement to expand the constraint beyond what you have already defined within the soft constraint, you can use disable soft. It kind of works similar to the constraint mode construct that we are going to see in the next few slides, which is used for turning on and off the hard constraints. So we have been looking at the inline constraints. So this just we will formally define it once and also look at few sort of quick quirks associated with the inline constraints. So whenever you have a constraint that is very sort of transient in nature or is very test specific, then you don't want to put it as a part of your overall transaction. You put it as a form of inline constraint. Okay, and this is something that typically you do it outside the scope of the class declaration. Okay, and this accomplished using randomize with construct, right? That's how you declare the inline constraints. And take a note that as we have already been calling out, that you add additional constraints to what's already defined in the class, right? With inline constraints, you're actually adding more and you are not overriding. Okay, so whatever the constraint that exists within the class, along with that the inline constraints gets added up, and it's not replacing what exists within the class, and hence if they can cause inconsistent constraints, and this can result in failures as well. Okay, so that is the so they work as additive hard constraints. So inline constraints are additive, they add to the existing constraints, and they are the hard constraints. So I mean, we have looked at various examples, and we have to, whenever you do the randomize, you can pass with, and in the curly braces you can define additional constraints that will be added on the top of the class. And so only one specific item that we wanted to really point out over here is when you do the inline constraints, actually inline constraints can also reference the local variables. The local variable meaning if I have this task body and if I have defined a local variable, and sometimes what can happen is that this local variable is trying to constrain a size, constrain another variable that's present at the class level. So for example, in this case, like in the class my item, I have another variable called size, and that variable I want to constrain to the value that's present over here in the local variable, which I might feel convenient to give the same name. And when that happens, and when you do this inline constraint of saying that local item dot randomize with local item dot size equal to size, then this could mean like there could be some confusion in the overall way the constraints get constructed, because this constraint, as we talked about, since it's additive in nature, it has access to the variables present within this particular class. So in order to resolve the scope, what you need to do is you need to use a local keyword, and when you say local and the scope resolution operator size, it allows the inline constraints to access the variables defined within that particular task or function where it's getting called. So this is one additional point that you want to take a note. Okay, so we have been looking at the random and Randc variables. We are looking at the constraint block and various operators that we can utilize within that particular constraint block. And we have also looked at, like for example, the concept of soft constraints. So we have been looking at constraint block and what can be done within that. Now we will look at from the outside of constraint block, how we can deal with it at an object level, how we can modify the behaviors, some of the behaviors of the constraint block. We'll look at it, and we'll start off first with the rand mode. And the rand mode method can be used to turn on or off the effects of randomization on the individual properties of a particular class. Okay, so if you want to exclude some data members from the effects of randomize, then you can do it with the help of rand mode. So when you say rand mode 0, it turns off the effects of randomize. Okay, but an important point to note is that it does not turn off the constraints on that variable. Okay, this is a very important point. So when we say rand mode 0, the effects of randomize, so it won't do the randomization. But when you call a randomize with a rand mode of 0, then what happens is that particular constraint that you have on the variable behaves like a checker. Okay, so it will, in other words, what it will does is the randomize wouldn't assign any random values when you are calling the randomize with a rand mode 0, but it will check whether the value that exists in that particular variable satisfies the constraint or not. And if it doesn't satisfy the constraint, it will still return 0. Okay, if it satisfies, then it will return 1. That is, you could take a particular variable, assign some legal value, turn off the rand mode to 0, and you call randomize. Now the constraint will act as a checker and see whether the value that you have assigned is satisfying the constraint that has been specified. The constraint would get turned off, and hence still the randomize method will check if it's a legal value as per the constraint, it will return 1, otherwise it will return 0. So this is how the rand mode behaves. So I'm showing you an example over here. So we have a class packet, and we have bunch of random integer variables. We have source value, destination value, and then we could have other declarations as well. And then we are creating object handle as well as the object in the same line on this 170, and then we are saying packet a dot rand mode is 0. Okay, so here what we do is we turn off the rand mode for all the variables. Okay, and then it will, if you just do the randomize, it will just check if there are any constraints, and it will just do the check. Or you can enable or disable the randomization on a very specific variable. So for example, you can do packet a, and using the dot notation, you can access the properties saying packet a dot source value, a particular variable, and you can say dot rand mode and turn the rand mode for that particular variable on. Okay, and then you can also find out whether a rand mode for a particular variable is turned on or off by using the rand mode in the function type of a context. It can be used both in a task as well as a function type of a context. You can use it in the function type of a context, and you can say return. I can declare an int variable return and say packet a dot destination value, and I can say rand mode. Since I've turned off all the rand mode, this particular thing will return a value of 0. Okay, so this way I can query the current state of the rand mode for a particular variable or for an entire class and make appropriate decisions based on that. The second question that will come to our mind is that what is a use case, right? What is a use case for such a why do we need to really turn off the rand mode? So what can happen is that you can have a very huge configuration objects, and you want to do a selective randomization. Selective randomization meaning you want to set few specific variables to a very specific values, and then let the other values of the particular configuration get randomized, right, in order to sort of save on overall performance as well. So you don't want to unnecessarily randomize everything, or your application requires such that you need to randomize certain values to a specific configurations because those are what you really want to test. Then you have two ways to do it. One is you could use randomize with, and then you can assign those fixed values to the random variables and call the randomize, and that will also work. Or you can selectively set up the like turnoffs, right, and then set up the values to whatever you want and then call the randomize method, and then in that particular randomize method it will anyway just check it, right? So one of the example that I want to show you guys over here is that we have this class C and we have two random integer variables. There's some constraint saying A should be less than B. Now what we can do is we declare the class handle, and then we are creating an object for that particular class handle, and then we are saying we are assigning some fixed values to these random properties, and then what we are doing is we are saying that handle.a, that particular property rand mode, we are turning it off, and for B also we are turning it off, and we call assert this cb.randomize. So now if I see A is equal to 5 and B is equal to 1, so 5 less than 1 will evaluate false, so the constraint will result in failure. So this randomize that I'm calling will result in failure, because as we talked about, when we turn off the rand mode, the constraint is still active and it will act as a checker, and it will check whether this particular constraint is holding up, and since in this case it's not holding up, it will lead to a failure. Okay, so this way when you want to do selective randomization, you can either use with or you can use rand mode, and using that you can turn off the constraints. So typically some of the times when you want to do the selective turning off, it's done in function called pre-randomize. We will look at it as to what the pre-randomize does in the next few slides. So with the rand mode, one of the challenges that you might face is that you might turn off a particular rand mode for a particular variable, and then you might forget to turn it on. Okay, to prevent that, there is one more alternative way that can be used, wherein when you call the randomize, you can pass the set of variables that you would like to really randomize, and when you do that, what happens is the rest of the variables are treated as state variables. Those are not touched by the randomize. Okay, and it expects them to contain the legal values. It won't change them, but it will still check using the constraints that have been defined to make sure that they are legal values. If they are not, then it will give the error on those particular values. So let's look at how it works. So we had this defined this packet class in the previous slide. So we create an object and we call randomize with some variables, right? So address kind equal to local and not of is control message, and after doing that, maybe we use this packet, and second time when we want to randomize this packet, we would like to hold on these values, but let's say I just want to change the payload. Then what I can do is I can say p.randomize and just pass the value of the variable that I would like to randomize. So I can just say payload, and then what it will do is now it will randomize the value of payload adjusting to the other variables, right? So other variables, it will take it as state variables, and whatever those values are, with those as a constraints, or within those values, whatever the other legal values that are possible for the payload, it will randomize it with those values, and it will generate a new packet, and then I can use that packet, and let's say I can then assign some more variable values directly to this particular class. And then what I can do is I can call just randomize and pass this null. Okay, so when I pass this null, what will happen is that it won't touch any of the variables, and but it will just do the check that whatever the constraints that I have defined, it will just do the check that the values that are present in all the random variables are satisfying the constraint. So it will do the check, because I don't know, I might have changed few things and I might have violated, so I can just do a quick check saying that a randomize and pass it as a null. And then let's say I want to re-enable everything and I want to go back to a fresh randomization. I can just say p.randomize and need not pass any variable over here. So when I do that, again all the variables that are present will get randomized. So this way, instead of using rand mode, you can pass the argument to the randomize to specify which variables you would like to randomize. So this is sometime useful. So if you use it properly, it also helps boost the simulator performance, because you are not unnecessarily randomizing all the variables. So we looked at the rand mode, which we were using to turn on or off the effects of randomize on the individual properties of the class. Now we look into the constraint mode. Okay, so constraint mode can be used to turn on or off a constraint. So if I contrasted that with the rand mode, the rand mode was turning off the effects of randomization on a particular variable, but it wasn't turning off the constraint. So constraint still acted as a checker to check the value that was assigned to those variables. But whereas when we use the constraint mode, we can enable or disable an entire constraint block, and if multiple expressions are present within that constraint block, all of them get disabled. Okay, and the rand mode we were able to control for the entire class, but the constraint mode we have to control it at the individual constraint mode level. There is no constraint mode call that can turn off all the constraints that are present within the class. So it has to be turned on or off at the individual constraint level. And similar to rand mode, constraint mode can also be used to control and check, right, whether a particular constraint mode is active or not. And when it's used in the to control it, it will act like a task, and when it's used for checking, it will act like a function. And typically the reason to turn off a certain constraint is it's to widen the total scope of the values that a particular variable can take, right? So constraining is constraining it. So when you turn it off, it sort of the overall scope of the random values that a particular property can take widens. A similar thing happened even when we turned off the soft constraints, if you remember. So same thing happens with the constraint mode. When you turn off a constraint, the overall values that it can take expands. That's the reason why you would want to do that. The other thing that you can note is the constraint block can actually be declared as static. Okay, so when you declare it as a static, then the constraint mode that you create on a particular object will have effect on all the instances of that particular object. So that is something that you might want to take a note at it. And let's look at an example to understand how this works. So I have this class packet, and then I am declaring this constraint called payload length, and I'm using some sort of an if-else logic to constrain the size of this particular dynamic array, right, which is of some u byte payload, which contains the number of bytes worth of the payload. So I'm using that to some logic to control the overall size of this particular dynamic array. And what I'm doing is I am creating an object for this particular, so for the particular class handle P. The class declaration is not there, but you can say that class packet P at the top, and then we are saying P equal to new. And now here I'm using the constraint mode in the context of a function to check if the constraint mode for this particular constraint block, which is C payload length, is turned on or off. So I'm saying if P and C of payload length, which is the name of this constraint block, dot, I'm calling the constraint mode, and this will return a value of 0 if it is turned off, and a value of 1 if it is active, right? And then let's say if it returns a value of 0, and then I want to so let's say if it returns a value of 1, then we say that the constraint is active, and if it returns a value of 0, then we go to else, and let's say I want to turn this particular constraint mode on, and then I use the same hierarchy, that is P and C payload length dot constraint mode, and pass the value of 1, and now it works in the task context and turns on this particular constraint, and then I can call assert P dot randomize. Okay, so when we are in this context, like let's say if I turn off this particular constraint, and then I call randomize method, then what happens is this particular dynamic array has to be newed explicitly. Okay, just because it is rand, it's not going to get some random value. You have to allocate it if you need it. If you do not allocate it, then by default this size will remain 0. This won't get randomized and get allocated to some size, right? Then it can become a huge array, and it could lead to simulator performance issues. So this will remain at a 0 if you do not provide the constraint on size. That's just a side point, but I'm just calling it out in the context of this particular example. So when you play with the constraint mode, you have to be careful. Sometimes you might turn off the constraint mode and forget to turn it on, so you need to take care of that. Okay, so we have been looking at the constraint block, the operators that can be used within the constraints, and then how to sort of turn on and off either the rand modes or the constraint modes, and the types of different constraints, the soft and hard constraints. Now we will move to the methods that are available, right? So our idea of the goal of this session was to understand the constraints and then understand the methods through which we activate various constraints, right? So we'll start off with the standard randomize method that we have been using so far. We have not formally defined it, so let's define it and understand it further. So when you call a particular object.randomize, actually what happens is it executes in 3 steps. So first, there is a built-in function called pre-randomize that gets called in every class, and it can be extended, and you can add whatever your user defined functionality within this particular method. So it's a predefined method. So you can say function void pre-randomize. Think of it like a virtual function that's already available, and you can fill in whatever the additional functionality that you want it to happen before a particular object gets randomized. So sometimes what happens is that you have to prepare certain state variables before the randomize can take effect. So certain queues might have to be kept prepared, which are going to be used while it is doing the randomization. Those all processing you can do as a part of the pre-randomize, and it gets called automatically. You don't have to do it. So automatically it gets, whenever you call the randomize before computing the new values, it gets automatically called, and you can override you can override this particular method and set up whatever the preparation that you want to do as a part of the pre-randomize. Then every class, as we have already seen, you have the randomize method, and it has a return type as int, and this randomize method returns 1 if it is successful, and then sets all the random variables that are present within the object to the valid values. Otherwise it returns 0, and whenever it returns 0, it means that the some conflicting constraint has caused the randomization to fail, and leaves the previous values. So whatever was the previous values that it had randomized to, it will leave it to those particular values. So sometimes you need to be careful. So in some simulators, the randomization failure, unless you have added an assert, it could be treated as warning, and it may end up using the previous value. So that is something that you need to take care. So randomize method, by the way, it cannot be overridden, and it implements the random stability with seeding. So we will understand what this means in the subsequent slides. What is this stability means, we will look at it. And whenever you do the randomize, you need to check it. So you can check it either if object.randomize, or you can just use a simple statement assert and your simple immediate assertion you can use. And once the randomize call is completed, there is another function that gets called automatically called post-randomize, and this can be again overridden, and you can do some sort of a cleanup. So sometimes what happens is you cannot solve some complex things only using the constraints. So constraints, you use it to certain extent as much as possible, and then you clean up the generated values using the post-randomize. So you tune it up to make sure that they are legal. So whatever complex things that you cannot solve using only the constraints, so you let the constraints solve to the extent that it is possible, and then inside the post-randomize you trim it and make sure that it meets your requirements. So that way this both the pre-randomize and the post-randomize functions you can utilize for preparing certain state variables that you want to use in the randomization, and then post-randomization, if you are not able to solve it completely and you want to tune certain variable values, you can do that in the post-randomization. So these methods can be utilized. So we have seen the class-based randomization so far, that we can define a class and do the three-step randomization process wherein we define the rand properties and define set of constraints and call the randomize to randomize the property variables. But sometimes you don't need such a heavy duty construct to do your job. You just simply have few variables and then you want to quickly randomize them. You don't want to really construct a class out of it. You want some quick results for doing something simple. Then you don't really have to use the whole three-step process. You can use this built-in function called standard : randomize, because the built-in function of the randomize that we use is always associated with a class, as we saw in the previous slide. So if you do not declare the variables within the class, then you cannot use the class.randomize a type of a function. So but you can use this randomize function that's present in the built-in package called std, standard package, which is a built-in package of SystemVerilog. You don't even need to import it, and then to this function you can pass one or more variables along with an optional constraint block. You can pass it, and then the standard and this is standard is a package name, and then the scope resolution randomize. It enables users to randomize data in the current scope, that is wherever that you are within a task or function, wherever you are trying to randomize few variables within that current scope variables, you can take and randomize without the need to again define an additional class, instantiate, create a handle, instance the object and call randomize, right? So you don't need to do that when you have some simple requirement. Let's look at an example. So here we have bunch of variables called address and data, and I'm writing a function generate stim, which is for generating stimulus, and I am just saying standard randomize address data read write. So now these variables will get randomized as per the whatever the legal values that are allowed by this particular data type, and return once if it is successful and sets all the random variables to the valid values, whatever that particular data type can take. You can also define an optional constraint block within the standard randomize. So here if you look at the second example on this line 454, so I am able to call standard randomize a set of values, and I am using this inline constraint mode with, and I am saying a less than b, and then a plus b should be less than some length, right? So I can define this way constraint block, and then the standard.randomize standard scope resolution randomize function will take the constraint block into consideration, and then select the random values as per the data type that we have defined, which satisfies this particular constraint block, and place them in those particular variables. And again it will return 1 if it is able to satisfy them, and if it is 0, similar to the way we call the randomize. So when you need some local variables to be quickly randomized, then you can use this function as well. So as we saw that for the quick randomization, we could use the function that was present within the built-in package std standard. But there are also certain built-in system tasks and functions that are available which can be utilized for the discrete variable randomization. So we look at few of them. So we have this function called urandom that generates an unsigned 32-bit unsigned random number. It generates a pseudo-random number, and it uses the random number generator to make sure that it can generate a same sequence of random numbers every time the same seed is used. So you can pass an optional seed, and when you pass this optional seed and you call the urandom, it will generate the same the same sequence of random numbers. So this way it helps you build a repeatable sequence. And if you wanted to generate a 64-bit random number, then you could probably say address equal to urandom comma urandom. You can concatenate two 32-bit to generate a 64-bit random number as well. So this way what I'm trying to show you is you can generate any width as well. And then you have the urandom range, which is similar to your urandom function, but allows you to generate a random number within a range, and you can define this min value and max value, and it will generate within the range. So you can note that the min value takes a default value of 0, so you can only pass the max value and still be able to generate a random number up to that particular value. Again, it's a 32-bit unsigned random number that it will provide within the range. There is a concept called the random stability. So we will talk about it a little bit as we go in the further slides. And this srandom can be used to manually seed the random number generator. So instead of passing every time I call the urandom, I can call the srandom and set up a particular seed at the beginning, and then keep calling these functions which will use this particular seed. Okay, so you can manually seed it. There are some seeding rules that are already defined within the simulator context as well, but you can do the additional control using the srandom function. So as we have been talking about the random number generator and then setting up a seed to ensure that it can provide a like a repeatable sequence of pseudo random numbers when you pass the same seed. Now when you are in the middle of something or up to a point, it stores the state, which is called as the rand state. You can query that particular rand state, right? And it will return, so as per the LRM, it will return a string of unspecified length and format. This is something that the LRM allows it to implement it in a simulator specific fashion. And if you can actually, there are some advanced use cases where for the random number stability, you can get a rand state from one particular thread and set it to another thread. I mean, I have not used it ever, but this type of capability exists. So, but in order to set the random number generator state, you cannot just set any value. So you need to get it from somewhere and set it for another thread or for another class or for another module. You can take it from one and set it for another. So it has to be a combination of get and set, but these functions are available. So we have been discussing sort of a procedural randomization, right? So there are two ways that you can broadly do randomization. One, that you create an object and you call object.randomize to randomize. Another with these methods called either the standard : randomize or the urandom range. And then eventually this random weighted case, you can helps you do procedural randomization. Procedural randomization means you are writing a task or a function, and within that you are randomizing few things. Okay, although this way of doing randomization is something that's not very recommended, but in few cases you can rely on this. The reason why it's not recommended is when you have do class based randomization, it's sort of easy to control the overall process of randomization. It has a very good structure. I can turn on, turn off something, I can override something, but those things are not possible when you do the procedural based randomization, because procedural based randomization is not in a way, it's not like truly object oriented randomization, right? So that's where it sort of lacks. But there are few use cases where you can utilize it. So one other construct that helps you do the procedural randomization is this random weighted case. So what happens is that you can define a rand case construct, and when you do the rand case, the case statement randomly selects one of its branches. Okay, it randomly selects. Now how does it selects the random branches is that you need to define a non-negative integral value that constitutes a branch weight, like similar to what we saw in the dist within the context of class-based randomization. The rand case allows the distribution in case of the procedural code-based randomization. So here when I say the branch weight as 3, 1, 4, then the probability of each one of these branches getting selected is this particular weight of the branch divided by the total weight. So that is 3 by 8 for this particular branch, 1 by 8 for this branch, and 4 by 8 for this branch. Obviously, as you can see, this branch has the highest probability of taking place, and you can actually specify a branch weight of 0 as well. The reason why you would want to do that is while you are debugging or certain things, you want to temporarily disable that particular branch, then you can specify a 0 weight instead of commenting, then that particular branch will not be taken. And you can actually, one of the very popular use case for Rand case that I have seen is you can do percentage based error injection in certain implementation of verification IP. Say you have a protocol and you are trying to implement different errors, and you want to pass the percentage with which that particular errors needs to be injected. As we have discussed in the past as well, there can be multiple errors that can be injected. So now you can specify with what percentage each error should be injected, and this particular branch there where I am showing you a fixed weighted numbers could potentially be taken from certain variables. And what we can do is, for this particular use case, we can just make sure that all of them add up to 100. So I've just taken one example. Specifically, I'm adding up to 100. So now this guy will do 10% CRC error injection, 60% credit error injection, and 30% some other error injection that could be specified over here, right? So this way you can do a percentage based error injection in the procedural context using the Rand case statement. So continuing with the like a procedural code-based randomization, we have one more construct called Rand sequence. So Rand sequence, I have not seen very frequent usage for this particular construct, because typically we do the sequence-based randomization using the UVM sequence, which we will look at when we go to the UVM verification methodology. But this construct exists and it's very involved. I mean, it is very strong. It has a lot of capabilities, and it's typically can be used in like a assembly language sequence or a network traffic generation. And the way this works is Rand sequence, when it gets executed, it generates a grammar driven stream of random productions. Okay, so what is that? We will look at it a little bit. We'll look at it with an example, but first let's understand what this means. So a Rand sequence grammar is composed of one or more productions. Okay, so each production contains name and list of production items. Okay, so we will correlate each one of them to the example. First, let's understand what this is. So when we say grammar, right? So if you have not been aware of like that BNF format, the Bacchus norm format, or for defining how certain things are decomposed further, right? So you declare something high level and you keep on decomposing that to the lower and lower. So that's how typically the language parsing is done. Okay, so that is the idea of grammar. So you represent something high level and then you keep on decomposing it to the lower and lower levels. That is a grammar at a very high level. So this, when we say production, we are referring to at one level what we are defining. So each production that at one level, how do you define, right? Can contains a name and list of production items, and production items are further classified into terminals and non-terminals. Okay, and non-terminals are defined in terms of terminals and other non-terminals. And terminal is an indivisible item, right? So terminal is when you execute something final. Okay, and the non-terminal, it just defines at one higher level that how a particular thing is composed of, right? And ultimately every non-terminal should be decomposed to a terminal. The finally something executable has to be created. Okay, and that is the one that really gets executed. And this rand case is a very powerful construct. We are not going very deep into it. It's one of the it's not very frequently used construct that I have seen, but this exists. And inside each of the production that we are defining, we can again use if else, case, repeat, break, rand, join in production definition, which can lead to creation of a very complicated sequences. So it's very powerful. If you do any processor type of verification, then you might come across the usage of rand sequence to generate random assembly type of a code. Let's look at one of the grammar as to how it works. So here what we are trying to do is we are trying to decompose, we are trying to create a sequence of assembly operations that we want to generate, the legal assembly sequences that we want to generate to test it. So at the top we are saying main, these are the production, and I'm giving a name and then I'm defining it can be composed of first, second or done. Okay, so these are this could be either a terminal or a non-terminal. Non-terminal means beyond that there is no more decomposition. Okay, so then first I am defining this particular terminal. This can be again composed of add or decrement. Okay, so this can be one of these two. And then if I look at add is a terminal because it's finally something executable. So this dollar display can be executed, right? So I am saying dollar display of add. Then a decrement is also a terminal, and this also, we are doing the dollar display. And this second one I am saying again it can be constructed of pop or push, and pop or push are again terminals because I have the dollar display, that is something that I can execute. Then I have done which I was using it at the first level, but that itself is a terminal because I am already doing something over here, right? And when I execute this particular rand sequence, so what it does is it can now pick, so it will generate something in this order. Okay, so it will generate first, second and done. So it will always generate in this order. Something needs to happen first, then second one will happen, and then done will happen. But when it picks the first, it can either pick add or it can pick this decrement. It can pick any one of them. If you see here, so when we call this random sequence multiple times, it can sometimes pick add and sometimes picks decrement, right? And the second one can pick pop or push. So I can see that it has picked pop or push, pop or push. Done, of course, here we are, since it's already a terminal, it will always remain done. So this way it randomizes at this level, right? And you can create a fixed sequence, which is a legal way of constructing something, because some things you cannot completely randomize, right? Like for example, an assembly instruction, there are few changes that you can bring in, but the order of fields have to be maintained, and wherever the changes that you can achieve, those you can define it as further productions and define that what are the possibilities that it can pick. So you can think of it like a graph, and it will keep on traversing different branches and select the different values in those branches and construct the entire the sequence that you have defined in your main production, right? So this is how the rand sequence construct works. This is an interesting construct. I mean, feel free to explore further based on LRM if it interests you. See, ideally when you build a constraint random test bench, you don't want a small test bench change to lead to a complete change in the constraint random stimulus generated, right? And we have already seen that with seed you can reproduce, but if you do a change in one area, then that does affect, because we are finally going to the same random number generator, and you are trying to get random numbers using the same seed. So if the total number of randomized calls changes, then obviously the way the stimulus gets constructed can change, right? So but if you want to minimize that particular change, the way the simulator does it is that it creates that the random values that are generated by one thread or by one particular object are independent of each other. Okay, so it uses a separate state to generate the random number for each object and for each of the thread. So this property of decoupling the random number generator for threads and the objects is called as random stability. Okay, and probably the term makes sense that Because of that, if I change in one object, the effect of it on the other object is minimized. It's not zero, okay, but it gets minimized. So and this concept of random stability applies to urandom and the urandom range functions, the shuffle, which is array manipulation method, the procedural rand case and rand sequence statements that we saw, and then the object and the process random seeding method. So using srandom, and then the object and scope randomization methods using randomize. The scope randomization method is that standard double colon randomize, as well as object dot randomize. Both of them they all have this support for the random stability. Okay, and using this srandom method, although the simulator takes care of it, but if you want to get a precise control and you want to control the the random number generator state, and you want to seed it explicitly for everything, you can do that. Okay, and in some very complex test benches where there is a high level of sensitivity associated with respect to each of the components, there are cases. They are not very frequent. There are rare cases where the test bench developers take a full control on setting up the seed for the random number generators in every object and thread. But it is rare. But it can be done using that srandom and that get_rand state, set_rand state. Using those calls, you can precisely control how much do you want to decouple. So you can additional decoupling you can do using these system level functions to achieve further random stability. So most of the time, I think like what we really do in most of the projects is there is a master random number generator, and the seeding of that we generally control manually. Otherwise also it creates an internal seed by itself, but we control it manually so that it is easy for us to reproduce the constraint random test. So when we run the simulator, when you run the test, especially like for example I'm showing it for the VCS, but the similar type of mechanism exists for all simulators. You call plus NTB random seed. So this information will be present in your simulator user guide. So you say plus NTB random seed equal to some number. This number you can generate through your own some Python scripts or something, and that number, it can be again any. So this Python and Perl programming languages have their own pseudo random number generator, so you can use that, and you can generate the seed value. So what happens is you develop a one constraint random test, and if that constraint random test has a huge random state that it is exercising, then you run the same test with the help of different seeds. So you take a same random test and you say I will run it with 50 seeds. Because it has so much of randomization built into it, with the different seed it's going to produce the different behavior. Okay, and that's how you catch the bugs. So that's how the constraint random verification becomes effective for you. So what you do is you take a very high with the test that has high level of randomization, you allocate more number of seeds for that particular test. A test that has a minimum number of randomization, like we talked about it, right? So a randomization can be randomization in terms of sequence, or randomization in terms of the individual parameter values that a particular transaction that you are creating as a part of sequence is taking. So how much randomization exists in a particular test? If it is randomizing both the sequence as well as the parameter values, then it contains high level of randomization. So if you run it with a more number of seeds, it's going to produce different type of behavior. So what you do is you take a Perl or Python script, and then you generate bunch of seed numbers from that. Let's say I want to run this test with 20 seeds, and it will generate 20 unique seeds, and then it will pass them in that particular command line. It will create 20 command lines, and each of them will contain these different seed values, and I will run all 20 of them. All 20 of them I am running it with the same test name but with the different seed values, and they will produce different behavior. And then when one particular seed fails, I will take that particular command line with that specific seed value. I'll rerun it with the waveforms or with the higher level of verbosity to get more information about the failing test and continue the debugging. Okay, so that's general way in which we do things when we run the constraint random regressions. Now like the finer control that we talked about, that I want to explicitly control everything in the test bench. Not recommended for every case, but let's say for some reason you want to do that. then you can do that. Like for example, in this particular class, I can say I will seed it with some particular number. I will say this dot srandom and pass certain seed value, and then I am saying packet of new and I'm seeding it with 200. And let's say here I'm not shown, I have called some randomization functions, and after that I want to reseed it differently in some other context. Then I can say p dot srandom 300. I can reseed it with a different seed value and generate it. So this way you can modify the seed state within the test bench at different points. If you think that you can manually better control the seeding, that is possible, and achieve higher level of random stability. There are some DVCon papers on random stability that if you are interested, you can read about it to understand further how to control, how to do fine grain control of the seeding within the test benches. But for most of the projects, I think, like as we talked about, if you pass the specific seed value to the master random number generator, that provides more than sufficient random stability with the built-in mechanisms in the simulator. So that's the whole idea. So I hope that's clear. Okay, so this concludes the section on SystemVerilog based randomization. So we saw three different categories of items in the context of the SystemVerilog randomization. The first category, wherein we defined a class containing the random variables and set of constraints, and calling a randomize function, right? So that is the first thing that we saw. And then within the constraint block, what are the various types of operators that are available, and then the difference between the rand and randc, how do they behave differently, and how different operators can be used within the context of a constraint block. How do we control the distribution of the random values that get generated? So we looked at those aspects, and then we came out and then we looked at when the inheritance is applied to the constraint, how does it behave, how we can add new constraints, and then how we can override an existing constraint using the same name. And we also saw, for a quick things that are not you don't want it to become permanently part of a class, you use the inline constraints, which also act as an additive hard constraints to the existing constraints. We saw the concept of soft constraints, which you can use it for the default value. And then we went into a details of various randomization methods that are available to us. Like for example, we generally have been using the dot randomize, and then we saw that there's a pre-randomize, post-randomize. In pre-randomize, we can do some preparation with respect to state variables, and in the post-randomize, we can tune the values, the random values that are generated through the dot randomize call, and how they get called in order. We saw that that's the second part of it, how the process of randomization itself works for the class-based randomization. So one is we have this object-based randomization, and second we have the procedural randomization. So in the procedural randomization, in any task or a function, if you want to do the randomization, how do you go about it? And in that context, we saw the built-in standard package has the randomize method, and then we saw a bunch of system tasks or functions called urandom range. We looked at those, how we can use that for doing quick randomization within the context of task or function without actually having to go to use the full object-based three-step randomization. So we looked at those, and then additionally we saw how the procedural-based randomization can be strengthened with the weighted Randc statement, which is very useful if you especially trying to do like a percentage-based error injection type of an application. The Randc is very useful for a procedural randomization. And we also saw this advanced construct called rand sequence, where you can define a grammar. That grammar you have to think of like a BNF format or like a tree type of an format, and you can define the order of the sequence of that you want to generate, and within each of those productions, how do you want it to randomly follow the path hierarchically. That can be defined within the rand sequence, and it can be utilized. And for this overall mechanism to work, the foundation is the random number generator that we looked at it. There is a master random number generator, and how the SystemVerilog simulator decouples them for every object and thread to provide the stability such that you change in one area of test bench, the effect is try to minimize the effect. It's not a zero. If you do some change, it's going to have some effect, but how do you minimize? We look at it using the using the seed control. How do you minimize that particular thing? How does the simulator minimize? We don't minimize. How does simulator minimize the effects? And how with certain functions like that srandom, getRandState, setRandState, you can take a manual control on the random stability and control it further depending on how your test bench is structured. And we also looked at the how the practical approach of how do we control the stability by passing the seed, and how do we run the same test with a multiple seed. This is a very important concept, that you run the same test with multiple seeds and it produces a different behavior. That's the main benefit of doing the constraint random verification, with which you result in fewer number of tests. The same test, you now run it with different seeds to get the different behaviors, and how that particular test fails. If you pass the same seed value, it will reproduce the same behavior unless and until there is a big change in your test bench. So if there are small changes, more or less it will reproduce the scenario, but if there's a big change, then of course it won't be able to reproduce it. How that is accomplished using the built-in RNG, we kind of looked at it. So this concludes the SystemVerilog randomization part, and this is a very important topic. I hope the concepts are clear, and we will look at it further. We will look at its further usage when we move on to the further projects development section. Okay, so thank you for listening.